to you. Do we want to act? Oh, this is actually installing OpenShift and stuff. I'm going to get rid of that. But I'm going to turn it over to you here because you're going to talk about how you built the Docker containers? Okay. So I'm going to change this to building Docker. And then should I leave your, so here's the post, is that the CPM thing?
Yeah, that's just a link to it and an introduction to it.
Do you want to give the architecture first?
Yeah, that's fine.
Yeah, let me give you the, I think that, and then I think I'm going to delete the commons slide, or should I leave it? I think that's way too much propaganda. Okay, so I need to get rid of this. I'm going to leave upstream first because you're an upstream first company as well. I don't like that one. Am I doing it on back? Oh, it's charging. Okay. I'm the first two. So I tried the secret one. That one doesn't work unless you've already defined the secrets, right?
Yeah, you have to define the secret first.
So this one works. You don't have to define the secrets first with the environment variable ones. That one just worked out of the box.
Yeah, that's good because when I built that, I wasn't building it to run on OpenShift. And the person
Right.
DreamWorks was interested in this, and that guy was like wanting to run it outside of OpenShift. So this container will run in or outside.
Out of open, and it works.
So yeah, so that's awesome.
Yeah. Bonus.
Something works.
Exactly.
Truth in technology.
Oh, so actually I should open, that's the other thing I should have open here. If you don't mind, is I will go here and I will go github.com and then it's crunchy data.
How big is the crunchy data?
And then you're just the first one there. So I'll just actually, I'm going to go here because then, okay, so now I need to do my font checks.
That's a good point because I've got the
Yeah, you can take, I'll unplug in a second because it worked to do something, and then you'll try yours. Yeah.
Online later today.
Yeah, it's actually online now. I should actually put a link into the slides. Hold on. Just give me a sec, though. I want to see if I can turn off the lights in the front. So that font is big enough if I can... Yeah. Is that okay with everybody if we leave the lights like that? Because that gets rid of all the glare on it makes the slides easier to see. Okay. You want to take the video cable and jack in? No, just take it. I'm done. Do you need the network cable? No. Okay. I just want to keep that. Go ahead. Just pull. It's not. There you go. Yeah, exactly. And if you want, I'll walk to the back of the room. I just want to put. I just got a Windows 10 box as well. Yeah, are you going to do any command line stuff?
What would you want to do? No.
Okay, then you're fine. I think. Well, this is kind of small. I bet this line right here. Let me go to the back. Not that I think we're going to fill the room anyway, but. Yeah, that line with my old eyes is kind of, it's hard to read anything on the left, and it's hard to read. So if you can increase the font size for that. Is there a way to? Oh yeah, just Control plus. One more. That's good. Is that okay? Can you see enough? There you go. Yeah, that's much better. Okay, should I take the video back? What time are we at?
10:30.
Yeah. Oh, we got 20 minutes. Okay. We get some water. Did you buy that?
No, it's not mine.
No. Maybe we should get rid of that then. Unless you want to drink somebody's backwash.
No.
You're not really interested in the backwash?
I walked past you guys.
On the street? Not so excited about that.
Not at home anymore.
There's in the back. I'll go take it there. All right, so I got that. Got that. I don't need Bitly anymore. I got that. I got that. Oh, I need to make a new project. Okay. I was gonna. It's okay. All right, I think that's, okay, the mic's on now. All right, so So the question, all the other questions that were asked, I'm looking at the camera now. All the other questions that were asked so far, meaningless. You didn't need to hear them. The question that this young gentleman just asked is, where does all the magic happen that allows, in normal streaming replication, there's like SSH keys and all this other stuff that happens. How is that happening here? And that's why I said OpenShift doesn't know any of that. That's not part of the OpenShift part. OpenShift just knows how to spin up the replicas. It's the Docker image builder, Jeff, who made it so that when they spin up, they could do this kind of stuff. So now, Jeff.
Yeah, this is really simple in that there's no SSH key generation required for this type of Postgres streaming replication. The only thing, because it's using just the Postgres protocol, so what happens is when a slave connects to the master, before that happens, all I do is execute PG-based backup to create that replica for that slave container, and then at that point just start up Postgres, and it's in a replication mode. The master is doing a protocol with that slave to establish that replication protocol. So there's no SSH key generation required in these examples.
So maybe this is a Postgres ignorance on my part. There's no encryption between the master and the slave.
So the question was, maybe this is ignorance on my part. I got to get that part in, just because it's important. But so there's no encryption between the master and the replica in this case. And then wait, Jeff said no, but then Josh looks concerned about that statement.
You're not using an SSL connection?
There is not an SSL connection between the slave and the master. I'm just using a straight SQL connection. Yep.
It's easy to fix. It is not currently doing that, but as soon as Jeff leaves here, he promises me that he will make a new Docker container. No, it sounds like it's an easy fix. You would basically just have to put the certs on the different machines, right? In the Docker image itself.
I believe Postgres gives you that option, but I didn't choose to do that with this example. But the way I would fix it is I would go into the bash script in that container, and whenever it goes to set up the connection, that's the point where I could tweak the configuration of the replication. By default as well, this is using asynchronous replication instead of synchronous. So those kinds of configuration changes are possible either by tweaking the way I did the bash script, or I give you another avenue with this in that I let you mount a local volume that contains your own Postgres.conf and PGA, HBA conf files that are local. So you can even override the entire Postgres configuration using a set of external files. And that's just a Docker volume, a config volume that I'll let you have the option. You can either mount that and put something in it, and if something's in there, it'll use that. Otherwise, it'll use the one that gets pre-generated. The environment variables that Steve pointed out are another way of you tweaking the configuration that is generated by default. But you have the option to completely override the Postgres configuration using your own local config files.
So maybe you'll cover this, but I'm just wondering if there's like an OpenShift way. Like obviously, because the image is immutable and often public, you don't want to put your cert.
Yeah. It's not public. By default, the only traffic we route is HTTP traffic.
Well, sometimes you would go get the official public Postgres.
Oh, right.
Yeah. Typically, you would mount any kind of certificate store as a Docker volume so that you've externalized all those keys.
And we also have one of the volume types that we've also put in, it's in OpenShift, it'll probably get pushed back up into Kubernetes soon enough, is a secrets volume. Right, so you can mount that everybody can make a claim to that volume and get those secrets inside. It's a separate volume claim. So we have that as well.
I know your secret.
What?
I know your secret.
You know our secrets now?
Yeah, because you have hard-coded the home path to just MC crunching data where it's in list. So you might want to make that into an environment variable.
Yep. Yeah, there's probably...
You have to leave now, sir.
Yeah.
Just kidding. So he said something that was inconsequential. I know you couldn't hear it, but it was... the young gentleman here was also making a suggestion about how we might want to tweak it so that the path was an environment variable rather than hard-coded in the image. I want to keep going because I don't know where we are on time. Oh, we have a half hour. Well, that's still a lot of time. We're good. So now, this young gentleman in the front, you couldn't hear because I didn't repeat it, asked, what happens when you scale up to 3? Funny you should ask that question. Let's do that. So let's go back to the pods. No. I want to go back all the way up. What happened to the screen? You know why? Because I increased the font so that you can see that. There we go. Overview. Ready? Here's how hard it is to scale up to 3 read replicas. So what we're probably waiting for here is these are Docker images. So what has to happen is we have a master, and then we have a bunch of nodes that actually run the Docker images. If that node has not pulled that Docker image down already, it's got to pull down that Docker image and then spin it up. So we're already at 2 pods running, I think. Or did I just go to 2? Or did I not go to 3? Okay, there we go. So now I got to wait for it to scale to 3. And so that's what we're waiting for right there. We're waiting for, the object has been modified. Oh, there, it's 2. I've never seen that error before. Close.
Welcome to live demo.
I know, exactly. Yeah.
Is there any way in public OpenShift to ensure that my replicas end up on different physical hosts?
Yes. So the question was, is there a way that I can actually make sure that my replicas end up on there? Now we have 3 pods running. So that's all it took to get your 3 running. We'll do the data in a bit. But I'll answer your question in a second. Josh, I just want to show one thing. Here's the 2 that just spun up. We have to now spin up Postgres, right? So I want to show the logs while it's going, right? So that way, because I can't show that it's replicated yet until that actually finishes. The question that Josh asked again was, is there any way to make sure that they end up on different hosts? And yeah, that actually can be controlled through your deployment. Actually, through the cluster admin, they can set policies for how the deployment of Docker images happens or how the deployment of containers happens. So you can do things, it's actually a set of rules. You can have it as simple as disaffinity. I want you always to pick one that doesn't have one on it already. So when it goes through all the nodes to say, this is the scheduling part that we talked about, that Docker doesn't handle by itself. So you say, I want those 3 replicas. Okay, I've got 4 nodes. This one's already got a master, or this one already has a slave. Where am I going to spin up the next one? One of those other 3. I've already spun up the 2nd replica. I want to put up the 3rd now. Where am I going to put it? I have to put it on one of the other ones that don't have it. So that's a simple disaffinity rule, but you can also set things like, but I all want them to be in the same data center, right? Or I want them all to be in different geographic data centers. So do a disaffinity rule for data centers. You can also say, I want the one that is not on the same host that has the least amount of CPU and the most amount of memory. So it'll go through and start finding nodes and then do rules based on that. So it should be up now, right? Did we watch it do it? Yeah. So now I'm on another one of the new ones. Here I am again. That. Can you see that in the back? Once I get to it? Yep. There. Right? And, hold on a second. Just to show that they're actually really talking to each other, here's the master again. Here's where I copy and paste again. Can everybody, that's probably pretty, can you see it now? Oh, does copy and paste not work here? Is it Control-Shift-V here too? No. I thought, oh no, I didn't. Let me try one more time. Nope. Okay, you guys get to watch me write SQL on the fly. Thank you, pair programming, love it. And I don't even sit next to you, that's the best part. There, done. So that, I inserted it into the master. Now this is the part where Jeff gets nervous. What?
Backspace, 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 all the way. Table, space, test, enter. Semicolon enter here.
I think you're so smart. Okay. There. So that's on the, that happened, that's all set up and live. So now I have, so what's, okay, that's enough giving him attention. Don't reward him for his insubordination. Okay, so if I go back to this again, right, and make this smaller. So I think, first off, this is where I think, did I not make it small enough? One more, there we go. One of the things I really want to point out again here is, I would never be able to do this if I was trying to, or I might be able to do this after like 5 days worth of yak shaving, and I'm sure I would set it up wrong, and I would probably give up in the end, because I'm not going to spend does everybody know what I mean when I say yak shaving? This is a Linux conference. Come on, really? Okay, well that's right, I think I'm on a BSD list, I think. But the yak shaving is the idea, I'm going to tell it now for everybody since we have time. Yak shaving is the idea that you want to check your mail at the end of your 100-yard driveway, and it's the winter in Manitoba. So it's freezing outside. So you're like, oh, I better put a sweater on before I go get my mail. Oh, I don't have a sweater. Okay, I guess I gotta get a sweater. Oh, I can't go to the store, I gotta make a sweater. Do I have any yarn to make a sweater? No, I guess I better go spin some yarn. Do I have any wool? No, I don't have any wool. So I guess I better go get some wool. Okay, I better go outside and shave my yak. And so you spend the whole day shaving your yak, and you still haven't gotten your mail. Right? Which is a typical problem for developers a lot. Right? I really just want to write an app that has a database and a web tier, and I want the database tier to be replicated. Okay, well, spend 5 days setting up a Linux VM, and then you're going to start playing around with first installing Postgres, and then you're going to play around with how you're going to, and if you're 5 days later, you're frustrated, and your boss is coming to you and saying, where's that project I wanted? And you're like, well, I'm still monkeying around with Postgres files. And that's when they say, use Microsoft SQL Server, because I don't want you spending all this time monkeying around with config files. And then you're sad, and then you quit your job, or you become alcoholic. Yeah.
Okay, when you created the other replicas,
Yes.
did it copy the data from the first replica or from the master?
So the question was, when it created the other replicas, did it copy the data from the others, from the master, or
The first replica.
or from the first replica? No, this is typical like master replica replication, where the new replica comes online, it checks in with the master and it says, where should I be? And then it proceeds to read from the master and make itself like the master. Is that correct? That was just a fact check from the guy who actually knows.
I like that.
Yeah.
So what happens? Doesn't do that.
What?
MySQL doesn't do that.
We were not going to get into that other inferior database that begins with a Y and ends with a SQL. We're not even going to mention that on hold. That's a great project. I don't understand. I've been a PostgreSQL user for 10 years now, and I understood why people use MySQL because it's really easy to set up. This is not Red Hat speak at all. This is off myself because I wasn't even. But I just never saw a reason to use it. Personally, it just never. I wanted transactions, and I wanted stored procedures, and I wanted triggers, and I wasn't willing to give that up, and it was never that much slower that I needed to give it. I'm not Google scale or whatever scale everybody thinks they need to be at. Yeah, you had a question.
What will happen now if the master fails?
In this scenario, bad thing, right?
Or it fails for a short amount of time, say network disconnection.
There's a network disconnection. Nothing like that ever happens in the real world. So the question was, what happens if the master fails, right? Or the master gets disconnected? Jeff?
Yeah, right now, there's no automatic failover happening for you. You're going to have to, as a DBA, you're going to have to get in and trigger failover to one of the
but the master would respin itself back up.
Yeah, well, that's true.
So if OpenShift can see that it's down, because there's lots of different, we used to say going down, and that used to mean something very particular, like about what it meant that the database was down. But there's actually lots of different states of down, right? So if the OpenShift cluster or the Kubernetes cluster can't see, if that replication controller says there's supposed to be one of these, and it's not up, it will spin up a new one if it can't see it at all. We also have liveness checks, like a ready check. I don't know if you've did you define one?
No.
OpenShift actually has the ability to say, hey, I know you're up, the container's actually running, but are you actually working? So you can define a probe that the cluster will keep hitting and saying, is it working, is it working? If it's not working, it'll spin up a new one and bring down the old one. But I don't know what will happen in terms of, if I bring up a new master with no data in it, what I'm assuming is going to happen, because this is the problem with using an empty directory. Right, there'll be no data. If we were using some other data directory as the PGSQL data, it could come up and then say, oh. Sorry? And all the states will replicate the data from master. Yeah, and then you wipe out all your data. So this is not a production setup here for anything that actually matters. Hold on. Wait 1 second. Yeah. Yeah.
Oh, I will be talking on Sunday about automatic failover.
Okay, so on Sunday, Josh will be talking about automatic failover with containers?
Yeah.
Oh, with containers. So,
Yep.
Jeff should attend, so that I can give a better talk next time. I blame Jeff that I couldn't answer that back.
One thing, that's a great question, best question of the day, in that it depends on how the master fails. If the node or the physical server that you've deployed the node to, let's just say, goes up in flames, at that point, you need to have made sure that your slaves or your replicas are running on separate physical hosts, and you're going to have to make a decision. Can I restore that server? If so, Kubernetes, when you start Kubernetes back up, it'll try to restart the master, and things will come back. But if the server that's on just completely is toast, then you probably will want to trigger one of the slaves to become the new master. But you're going to have to do that manually currently with the way these containers are constructed today. So you as the DBA would have to say, okay, I want that one to become the new master. Or you're going to have to go to a backup, create a new node somewhere else on another server, and call that one the master. But when you do, you're going to have to reconfigure this cluster all pretty manually at this point. I'll show you another project here soon that does this for you. To a certain degree, but that's a great question, and it's one of the downsides to using the empty dir volume type, okay, because it sets on that physical server, and that empty dir volume is managed and provisioned by OpenShift on that server. The upside is high performance. You directly are accessing local disk. If I make the choice or the decision to deploy all of this on, say, NFS volumes, then all of my Postgres performance deals with the latency or whatever of that network storage. So that's the architectural quandary or decision that you need to make when you deploy this is, am I deploying for ultimate I/O performance? If so, I'm probably going to use empty dir and deal with if I lose a server, here's my procedures to reinitialize this cluster somewhere else. Or if performance is acceptable using whatever network volume type that Kubernetes supports, whether it's Amazon or Google Cloud Storage, those are both options, then you probably would go there because now you have the ability, you have a lot more resiliency. So that's a great question, and it's one where when I was writing these containers, I can't answer that question architecturally for everybody because everybody in this room has a different problem they're trying to solve. But I did want to make sure that I could make the empty dir volumes work because I know a lot of people are going to say, man, I got to have ultimate I/O performance. So as tempting as it is to just say, I'm going to always use NFS and not have to deal with that problem, a lot of the thinking, at least in this project and another one here I'll just briefly introduce to you, it's using empty dir for a reason, and that's to give you the highest I/O bandwidth performance.
And it's not a simple one either. The other thing that Jeff was talking about, like when he said configuring it so the others become the master, OpenShift and Kubernetes, as soon as that pod dies, because the replication controller says there should be one of these running, it's going to spin up a new master right away, right? And I'm assuming that the replicas will try to reconnect to that new master that just came up, and it'll say, I have no data. Make yourself like me, and you're going to wipe out all your data. So this is not, I'm not showing like ultimate production scenario right here, but I'm trying to show something that I don't think any of us, most of you had probably never seen before, right? And some of the advantages to using this kind of architecture. More work would have to go in, like, and you could engage the crunchy people and engage the OpenShift people to figure out a better way to do that. Wait, there was a question in the back, and then I'll get to you. Is it going to have, no, the pod will be completely different names, but what will stay the same is the service name. And that's why the replicas are actually reading through the service rather than directly to the pod, right? So it will work because it's going to talk to the service, and because you put the service in front, it doesn't care what's the actual pod name behind it. Does that make sense?
How does the standby talk to the service?
What?
In the back end, when you connect to the Postgres, the back end connects to the IP.
Yeah,
How did you trick that?
yeah, everything uses the service name, and the service name is the IP entry point that everything can find everything through. So a pod, in this case, whenever I create the replica, I'm passing in the master service name. And if you look inside the pod,
I'm going to show them right now.
okay, Docker will actually always associate or give you a service name to IP translation.
Actually, it's Kubernetes that does it.
Kubernetes.
So Kubernetes and OpenShift insert, so it's going to be Postgres, right? Or is it going to be master?
Well, just cat out etc host, and you'll see something interesting there too. But that's a good example there of
right.
where.
So I'm in one of the replicas, right? And I probably have to make this bigger. Come on. Can you see it? It's fine? Okay. So this, when he's setting the slave is actually probably using that environment variable to get the IP address of the, oh no, is that, yeah, to get the IP address of the master rather than hard coding in, right? Am I right?
It's using PG master host and as the connection.
Where's that?
Yeah, it's 2 down.
2 down?
Yeah.
This one?
Yeah, it's using that. And you're like, okay, how does that get resolved? PG master, and yeah, so cat out etc host. No,
Host, sorry.
I nearly had a heart attack on that one. But
You're like, what? I'm made a fool of. You see it down there?
Well, I'm not seeing what I was expecting to see there. But anyway, the Kubernetes in this case, I keep forgetting what it's doing for me versus Docker, but Kubernetes actually...
oh no, Kubernetes, this service, in that service, that actually maps to the IP address.
Yeah, and it's getting resolved. That IP address is actually getting resolved by Kubernetes. But I'm referring to that as the connection host name.
So the reason if I had gone more into the whole OpenShift thing, back in that slide with the gold and blue, one of the hard parts about setting up Kubernetes is it doesn't include a networking layer. It expects you to bring a networking layer. OpenShift actually brings a whole software-defined network. And OpenShift runs its own internal DNS to do that kind of stuff. So it's doing it all under the hood.
So, but in the scenario where the master dies, it's not gonna read, the slaves aren't gonna reread that to reconnect, right? So does it shut everything down and bring them all back up?
No.
It's going to continue running back to the same IP.
Right.
Yeah.
No, but the IP of the service stays consistent.
Yeah.
Okay.
Right? Remember what I said, that IP address for the service never ever changes unless you delete it and bring it back again. But service IPs never change, and which is why you're talking to the service, not directly to the master. You're talking to the service, under the hood, OpenShift knows, and Kubernetes knows to reroute that to the pod that is actually the master. Right? But the IP for the service has never changed. That's the benefit of this framework. Right? That your end pieces don't have to care about pods going up and down. And the drawback in this case is we end up wiping out the entire data.
Steve might have mentioned it, but the service name for the slaves is actually a proxy, so it just implements a simple round robin. So your app, when it connects to that service and does a request, it actually just does a round robin against however many slaves you have. That's the other
Which is a good point. So this is the last part of the demo I want to talk about, because I want Jeff to show off his stuff as well. But go smaller, thank you. So this is for the app developers, or even for the SysAdmins, the DB admins who talk to their developers, which is a few of you. What is the other nice part about this architecture is, remember when we talked about the web tier talking to this? Oh, I promised you an answer to a question. Sorry, you have to wait about the nice part. You're going to miss the nice part now. Oh, go ahead. Taunt them too. Go ahead.
So in this configuration, if you did a manual failover, there's no way to get the slave, this new master, which was the former slave, into the PG master pod?
It is. So this is a whole Kubernetes thing. We need like a whole. So the question was, how could I, if I promote one of the replicas to master, how do I get that to respond to the service that is actually the master service? Kubernetes uses labels for everything, right? So if you look at the service right here, I'll click on the service, and if we look at the selector for that service says where the name equals pgmaster.rc, right? So the service knows what to route to based on that selector. So anything that says name equals to pgmaster.rc, that service will then start routing to that pod. So all you would have to do is, and you can do this in the version that I'm showing here, you just do OC edit, and you can edit labels. But if you go back and you look at your pods here, these 3 pods, if I click on these, let's see if it shows me the labels right here. Where's the labels? Nope, they must be under annotations.
Maybe.
No, where's the labels? All right, let me, I can't see it through the, oh, there. There's the labels, sorry. It's the new web configuration. The labels are actually all in blue on the top. So this one has the name PG slave RC. All you have to do is edit that label to PG master RC, and automatically that service would start routing to that traffic. You can manually edit it and do it. Without restarting the container, without doing anything else, you can just change traffic around by changing labels. So that's one of the other great benefits of this kind of architecture. Does everybody understand that? So that's the other, or let's say you have a misbehaving slave. It's working, but you're throwing a bunch of errors. When you go to the terminal, you see all these errors. So Kubernetes doesn't want to, OpenShift doesn't want to kill it, but you want to, and you don't want to delete it because you want to look at what went wrong. You can just change the label from PG slave RC to PG slave RC busted, and what will happen is the replication controller will say, oh, I don't have 3 of those, I only have 2. I'll spin up a new one, and the service will say, oh, I don't want to route to this because it's not the right name, but it'll still be up there and running and not dead. So you can go and do all the diagnostics. If you fix it, you can just change labels and do back again if you want. And, okay, so the cool thing, right, I was showing the cool thing. Is that what I was doing? It's not actually even a cool thing to show. It's just something that naturally happens. When you're writing your application, it's very easy now. When you're doing, if your application is doing writes, the only service it talks to is pgmaster RC. Right? I didn't have to do any weird configurations. I don't have to tell my programmers anything different. I say, this is your write service, and this is your read service. Right? All the reads should happen off the PG slave RC. You don't have to tell them to do, it's like, for me as a developer, that's such an easier way to think of what I'm doing. Oh, I want to read from the slaves and I want to write to the master. So those are the things I write to, and I don't have to worry about anything changing under the hood or how many replicas are up or anything like that. I know PG pools can take care of a lot of that stuff, but here if I'm just using, even if if you choose not to use it, it's there, and I don't have to care how many replicas are behind it, and I don't have to make my master do any reads at all. So my master can just handle writes exclusively, which is the preferred architecture, right? Yeah? Yeah? So it's just out of the box, we get that preferred architecture. And we get it easy for the programmers to know how to work with that preferred architecture. So. Down to 2, what? Why didn't you warn me?
Hi, man, you were on a roll. So you were covering everything I was going to talk about anyway. So. No, seriously.
2 minutes, we're done.
I'll just mention a few more things.
Go.
I'm about 2 weeks out from having a PG pool container that will work with this, by the way. Pulling that from this other project called Crunchy Postgres Manager. So probably in about a 2-week time frame, you'll have a PG pool container that will go along with this. So the idea there is you would deploy that into this environment. It'll know who the master service is, the slave service, and it'll configure PG pool for you so that it'll do smart load balancing. So your apps at that point would have one entry point instead of two. And that's going to actually be pretty useful for people. Also, backup and restore capabilities. People have asked about that, and that's probably another one where I'm pulling from another Docker project, again, the CPM project, a backup and restore. And that's just a simplistic backup and store where you can run backup on this, and it'll create a network volume will contain that backup. And I have to use network volume in that case because you want your backups to be kind of long living and whatnot. And you can deal with any kind of slowness to using network storage in that case. The restore will work, and basically it'll fire up this crunchy PG container. It'll look for some restore flags and also which restore archive you want to build your new container upon, and it'll basically pull down that archive to the local empty dir storage, and it'll start up Postgres using that. And that's another feature, a couple of containers that you'll see on this GitHub project pretty soon. And those are just what I would call basic features to get started. Allowing for a simple failover is definitely something that I've been thinking about how to do, like maybe exposing a trigger file location via Docker volume so that you could trigger it that way, and maybe some utilities that would help with managing some of the state. Some other points is this runs on CentOS and RHEL currently, so it's up to you which one you want to use. I supply Docker files to both. It uses the RPMs from the PGDG repo currently to do all this. It's where it gets its Postgres bits from currently. Crunchy itself has our own repo that we're looking at maybe offering that version up as well for a more secure or supported version of Postgres as well. So you could run these containers using that, say, in an enterprise scenario where you needed support. Other things is I put in here PostGIS and PG routing by default. So the size of this container is pretty hefty by Docker container image sizes, but the reason is there's a whole bunch of stuff in there that I just said, let me throw it in there, and if people need it, great, it's there, and if not, they can pare that out just by chopping it out of the Docker file if you wanted to shrink down that image size. But I've not found where the image size between 300 meg and 500 meg really matters for anything I've noticed. What else was there? I could talk probably for an hour just on the Postgres UID and GID configuration settings in OpenShift. The bottom line is Postgres needs and requires to run as the Postgres user. Out of the box, OpenShift generates random numbers for your UID. Well, that's a problem. If you just start this container up, it will die. Postgres will die and saying, hey, I need a Postgres UID to run under. I can't run under some dynamically generated number. So there's different strategies for that, and that's a security measure that's in OpenShift. But there's configurations in OpenShift that allow you to totally change that behavior. And you can say, no, OpenShift, run all of these containers as any user. You'll see in the Docker file I wrote where I specified the Postgres user to run this under. And also in the Docker file, you'll notice that Postgres is the last thing that runs, and it runs in the foreground, so it hangs there. And the reason for that is if it ever dies, Kubernetes will know that the entire pod has died and try to perform a restart. Okay, and that's just another thing that you'll notice if you look in detail.
Quick question?
I'm just wondering, does Postgres run as PID 1?
Not in this example. Okay, so what I do is I start up a bash script called, I think, start.sh. In there, it eventually makes its way down. So if you look, PID 1 is actually that bash script. Okay. Now, some Postgres examples will not work that way at all. But I'm still using a bash script in this example to set up some of these configuration options. And then the very last thing, the hanging process, essentially Postgres, that keeps that script alive so it won't exit. Don't have time today, but there's a whole nother project here. There's a couple of parallel tracks at Crunchy in terms of Docker work. This has certainly been a big one. We wanted to make it a way for people to run Postgres in an OpenShift container world, Kubernetes world. But there's a whole other project I did called CPM, or Crunchy Postgres Manager, that has web UI. It's Docker only. So it does its own level of orchestration. And it's for people that want to implement a purely on-premise Postgres as a service. But it uses Docker Swarm, and it's using Docker volume plugins and things like that to perform sort of what you saw today, except through a point-and-click web UI. And there's certain things I can do in that environment because I can control the entire host topology that I can't do in an OpenShift. So I encourage you to look at that project as well. In that one, for instance, I can do a backup and restore just point and click. And I can also do restores from things like PG-based backup. I can run PG Badger on any container. I can start up a predefined profile of clustering. And then I also built in there Postgres metrics collection using Prometheus. So it includes a whole lot of enterprise functionality as well. And so
we have a slide on it with the link to the Git repo as well. It's in there. So just to wrap up, we're in a time of container explosion. The take home I give to the Postgres maintainers right now, except for Jeff because he already knows this. If you don't know this already, some of the ways that Postgres does things were great back when Postgres was first built. It is not so good anymore in the world that we live in with containers. So it would be nice if we started to think about moving Postgres to being friendlier to containers and stop thinking that everybody's standing it up the way they used to stand it up before. I had a big argument with, it wasn't with the actual person, but like extensions. Please stop forcing it to be a root user or the Postgres user to install extensions. That is not the world we live in anymore in the cloud and container world. I don't need to be root or Postgres anymore to install an extension and still be secure from an administrator standard. The world is changing, and some of the ways that Postgres needs to change has to come along with that. And I get to say that now because I got the soapbox. Kubernetes and OpenShift get you beyond containers. Good times are ahead for you with containers and Postgres. Upstream first, so all the stuff that you're seeing is upstream both from Jeff's work and Red Hat's work. It's all done in open source first, and you have access to it right now to play with it. Reach out to me on Twitter or any of the other places where you can reach to Steve-O, even at redhat.com. You can't talk to Jeff because he refuses to use any electronic media. And that's it. Thanks, everybody. The reason I hate the X is because of a reason you're probably
Check. Everybody hear me okay? Good. Yeah, no, I count them. This is about how many there were on the last one, though. All right, maybe I'm wrong. I might be wrong. Right, no, that's true. True, true. Everybody hear me okay? Good. We're going to get started on time here in just a couple of minutes because we have a lot of material to cover. Told you so. Told you so. Gonna get a crowd for this one. Topic. Well, maybe both. Hmm? Good. I'll be started. All right, we have a lot of material to cover here. This is, yeah, everything's good. So this is actually a condensed version of a tutorial that I've given that's 3 hours. So we're going to be going through it a little bit quick, but feel free to ask questions. I'm going to go ahead and get started now so that we can get a little bit more time in because nobody cares about the front end stuff anyway. I'm Stephen Frost. I'm with Crunchy Data Solutions, Crunchy Data Inc., however you want to look at it. Nice. I'm a committer, major contributor. I implemented row-level security in Postgres 9.5, which was just recently released. I did column-level privileges. I've implemented the role system back in 8.3. So I've done a lot of different contributions to Postgres over the time. So we're going to go ahead and jump right into it, right? So the first big thing is a lot of terminology here. When you're working with Postgres, it's not quite the same as every other system, but you know, it's important to understand that terminology so we have a baseline. Yes, sir. Slides will be published, yeah. They're up, if you look for the Postgres Open 2015 slides, they're there. They'll also be posted on the wiki website for this conference once I'm done. So when it comes to Postgres, you'll come across terms such as a cluster or an instance. This is essentially one Postgres system that's running. We view that as a single postmaster listening on a single IP address and a single port, right? I mean, of course, we can listen on multiple IP addresses, but the idea is that it's one thing answering the call that comes in, right? And it's also one set of data files. Those data files can be spread out using table spaces. I'll talk about that a little bit later. The other big thing is that it's one write-ahead log. I'm going to go over what write-ahead log is later also. The general operations that you can do at a cluster-wide level, or start, stop, of course, initialization. That's also where all of your file-level backups are done at. So whenever you're doing a backup, you have to back up an entire instance or an entire cluster if you're using file system backups. There's other tools that you can use that allow you to do things that are smaller than that, but they're all logical backups. Streaming replication. So because there's a write-ahead log, the streaming replication is also something that ends up happening on a cluster level. And then there's a number of different objects that are defined at that level: users, roles, table spaces, and databases. Those are the kind of objects that exist at a cluster level inside of Postgres. When it comes to what is an actual database in Postgres land, so a database lives inside of a cluster, and you can have more than one database inside of a cluster. There's a few specific permissions that you're allowed to grant at a database level, which include connect, create, which is talking about the ability to create schemas, which I'll talk about next, as well as the ability to create temporary objects using the temporary bit. When you're talking about a schema, schemas are namespaces inside of databases. So this is kind of another level of this onion that we're working towards here. So you have, on the outside, you have the instance or the cluster. You then get to databases, and then inside of databases, you have multiple schemas. Schema level permissions include create and usage. So create means that you can now create objects, which I'll call principal objects, inside of the database. You then have the ability to use the schema with the usage option. Those permissions are at a schema level, so now you're considering like a directory, right? Whether you're allowed to modify the directory, add things into the directory, step into the directory. Those are what would be analogous to create and usage when you're talking about schemas. Table spaces are locations for other data files for Postgres. So if you've got 5 different mount points on your system, you could have 5 different table spaces that correspond to those different mount points, or maybe you'll have 4 additional table spaces along with the default table spaces that exist inside of the system to begin with. They are cluster level, and what that means also is that they can exist with multiple different database contents inside of them. So you can have one table space and then have files or tables or indexes that are from different databases on that system using that table space. Table spaces cannot be shared between instances or clusters, however, nor can they be moved between instances or clusters, right? They are associated with a particular instance of the system. All right, now I told you I was going to tell you about write-ahead log. This is a extremely important part of any database that has write consistency and also guaranteed write. So the write-ahead log is important because that's where every write to the database goes first. So whenever you do an insert or you do a delete or you do anything that modifies anything whatsoever in the database, we're going to write it into this write-ahead log first. We then, when you go to actually do a commit, we go and make sure that those changes have been committed to disk. That means they've been f-synced all the way out to disk. And only once that happens do we acknowledge the commit and tell the application that asked for the commit that we've actually accepted those changes and have committed them to disk and will not lose them after that. All of the changes to the write-ahead log are CRC'd, naturally. And the changes to the actual data files in the background, so we're talking now about the table spaces and the other files that exist inside of the system, Generally speaking, those changes are done in the background, right? That's what we want to have happen. We want to accept the changes through the write-ahead log, and then they get written out to the individual files in the background over a period of time during what's called a checkpoint, which I'm going to talk about next here in just a minute. One of the things that you do run into with a write-ahead log is that there can be a contention there, right? Because you have all of these different processes that are all trying to write through the write-ahead log system. That's why one of the things that Postgres supports is the ability to put the write-ahead log in another location. A lot of times what you want to do, especially if you're on spinning Rust, is put that on a dedicated set of RAID 10 disks, right? That way you get as much possible performance as you can out of it. Another interesting issue with the write-ahead log is that there's two different types of writes that we do into the write-ahead log. We do what's called full page writes, and we also do incremental changes. So a full page write in Postgres is 8K by default. So, and that's the first time we write out a page into the write-ahead log after a checkpoint, which I'll talk about next. That's going to be a full page write, and then any subsequent changes to that same page during that checkpoint will be incremental changes. In 9.5 that we just finally came out with, we are going to be compressing those incremental changes as well. So you'll actually get, your write-ahead logs will get smaller, or at least there's an option now to have them be compressed inside of the write-ahead log. Just to kind of hit on it again, what happens after we have a crash, right? So because Postgres has written everything into this write-ahead log first, what happens after a crash, so the database system gets killed or goes down for whatever reason, when it starts back up, it's going to look and say, okay, where was the last point in the write-ahead log that we had a checkpoint, right? A checkpoint is what we have when we actually have written everything out that was pending in the write-ahead log out to the heap files and synced them all, right? Once that's done, we make a mark inside of the write-ahead log saying, okay, everything's synced to this point. Anything that hasn't been synced after that checkpoint is what we're going to replay when the database system starts back up again. So when the database system starts up, we read through the write-ahead log and write all of those changes out to the heap files, because we can't trust that they were there because we didn't f-sync them ourselves. We didn't know that we told the kernel we have, to write this data out, and we know that it's done. So a checkpoint by default happens in Postgres every 5 minutes. What's happening here is that it's going through all of the dirty pages that we have and pushing them out to disk and f-syncing them. And what we try to do is we actually try to spread out the time that we're doing those f-syncs over that 5-minute period. So it can be forced for a couple of different reasons. One of the reasons that a checkpoint might be forced is that we've run out of room inside of the write-ahead log area that we've been provided to write more write-ahead log. Right, what this means is that there's a option, checkpoint segments inside of Postgres that I'll talk about a little bit later. But what's happening is that we don't want to just write out as much write-ahead log as we have available to the point where we fill the disk, because if the disk ends up filling up on your xlog volume, we can't accept any more transactions, right? Because we can't write out to the write-ahead log first, which is what we have to do. So there's a configuration option that says, okay, we're going to take and work with a subset of the amount of disk available, and once we run out of that space, if we haven't hit that 5-minute mark and have been able to, and are able to reclaim some of the xlogs that were already written, we will forcibly start in a checkpoint, which can be very expensive, and what will happen is that that'll immediately basically start f-syncing everything out to disk, right, so that we can get back write-ahead log space so that we can start accepting transactions again. So again, if you have questions, please don't feel too afraid to stop me, but we do have a lot of things that we're going to go through. All right, so the Postgres development group provides a set of packages both for Red Hat and for in terms of RPMs, as well as Debian-based systems. Those are really the principal ones we have now. There's also the Windows ones. I'm not going to talk too much about that because we're at SCaLE. Just saying. So both sets of packages from the community allow you to have multiple major versions of Postgres installed concurrently, and allows for smooth major version upgrades using the PG upgrade tool, which is really quite handy. In all of the systems that I run today, this is what I use, right? So I use everything from the PGDG, because those are the ones that are up to date, they're well maintained, they're supported through the community mailing list, and they're updated, the releases of them are updated in coordination with the Postgres team. So whenever a security change or anything is coming out, we coordinate that with all of the different packagers for Debian and all the Debian-based systems and Red Hat and all the Red Hat-based systems, as well as the Windows builds. So on a Debian or Ubuntu-based system, in this kind of an environment, it's app.postgresql.org. So you would add that into your sources list. You can use LSB release if you want to. And here it's pretty straightforward, right? It's apt-get, 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 right? Done. And we have the and then we've got the version installed. This is with 9.4, but of course 9.5 is out now. So if you want, just changing that to 9.5 should work just fine, and that'll pull in the latest version. In terms of how the configuration layout works when you've done this, so all the config files for a given instance or a given cluster, I was saying, live inside of a x.y, so that's a major.minor version. Well, in Postgres land, that's a major version, right? x.y is a major version. So 9.3 is a major version, 9.4 is a major version, 9.5 is a major version, right? And then inside of that directory under etc Postgres, because with Debian you're able to have multiple different instances installed as well, there's an instance name. So in this case, it's main, right? That's the default. So whenever you do this apt-get install, you're going to get a instance of whatever version, so 9.4 in my example, and that instance is going to be named main. All the data files end up in varlib, naturally, but it's varlib Postgres, and then that major version, and then the instance name. Binaries, so the binaries are common to all of the instances, right? There's only one set of major version binaries. Those live in userlib Postgres following that x.y/bin, and then there's a bunch of wrapper scripts, right? So if you're ever wondering, you want to go look at PSQL for whatever reason and you're confused on a Debian-based system why it looks like a Perl script, because it is, right? So it's actually a wrapper for PSQL, because this whole notion of multiple different instances installed on a system is not something that the Postgres utilities themselves directly support. So the Debian maintainers, which I think is fantastic, have come up with a number of wrapper scripts that provide the ability to have multiple clusters on the same box and be able to work with them very easily. Logs are pretty natural. Note that there's a difference between what I'll call normal operation Postgres logs and what are called the startup logs. So the startup logs are just kind of the bootstrapping of getting Postgres running has its own set of log files. In a Debian-based system, all of those logs go into varlog Postgres. It's a little bit different on Red Hat. I'll talk about that in a minute. And then there's one init script that starts everything on a Debian-based system for us. Don't ask me about systemd. I don't, yeah, let's not go there right now. So with these clusters, on Debian, those different instances are called clusters, right? And so these tools are all say cluster in them. So PGLS clusters gives you a listing of all of the different clusters that exist on your system. And that can be across different major versions as well as multiple instances inside of a given major version. PGCTL cluster is what you use for controlling Postgres. So on a system like Red Hat where it's not using these wrapper scripts, the command is called PG_CTL. I'll talk about that in a minute, but on Debian-based systems, you want to use PGCTL cluster, right? And that's what you can use to start, stop, signal the database. Generally, you want to signal it to perhaps reload files, reload the configuration files. And then there's a -- cluster option. So this is one of those cases that's kind of weird, right? So this -- cluster, that's 2 dashes, sorry, specifies which option or which cluster to work on inside of a Debian-based system. And here you can see I've got a -- cluster 904/main. So the way you specify it is always x.y/ and then the instance name for basically all of the tools. If you don't specify it, there is a default that's picked up and used, which generally is whatever's running on port 5432, which is the Postgres port. That's where the default is going to be. And here you can see that it also tells you what the data directory and what the log file is when you're using PGLS clusters. there's a bunch of different configuration options that are available. I'll talk about that in a minute when it comes to Debian-based clusters. All right, so now for a Red Hat-based installation. On Red Hat, you're using yum.postgresql.org, and this, whatever RPM-based system you want to use. When you install it, it will go ahead and initialize the cluster. You can run multiple different major versions in parallel. It's a little bit ugly, in my opinion, but it does work. This is how you can do a group install that pulls in all the different dependencies that you want. And then here you have to, on a Red Hat system, you don't get the database initialized. You have to do this in initdb yourself. So that's what you do after you get the actual packages installed. You have to do your own initdb, and then that will create the cluster for you, create the instance, and then you can use sysctl to start it up. All right, so on a Red Hat-based system, everything, all the data files and whatnot live in this varlib pgsql. So you don't have quite the same, it's not quite as convenient to have multiple different clusters. You don't get all of the cute wrapper scripts that you get on a Debian-based system. All of the configuration files that I'll talk about here in a minute live inside of the data directory on a Red Hat-based system, which personally I don't like, although that's kind of the way Postgres operates when you're using it, when you install it from source also. Binaries go into this user/pgsql-x.y/bin, which I find bizarre. And then the logs are in varlib instead of varlog. And there's actually two different locations. So you have a startup log that's here in this kind of major version directory, and then the actual regular operational logs are in data/pg_log on a Red Hat-based environment. I will fully admit I'm not a Red Hat guy, so take all of this with a little bit of grain of salt. I went through it and did it, and it's where I found everything, but just be aware of it. Oh, and you also need an independent init script on a Red Hat-based system for each of the different major versions you want to run. All right, so when it comes to configuring Postgres, there's kind of really four major configuration files. There's the main, what I'll call the main configuration, which is postgresql.conf, and that's where you configure a lot of things like how much memory Postgres uses, how much, what port it listens on, all of that kind of information. But then when you want to get into, okay, the question of how do I connect to the database? What do I do? How do I get users connected? What are they doing? So to do that, what you have to use is pghba and pgident. So pghba is allows you to control what authentication method is used to for the user to connect. pgident is for mapping users between, you may have multiple different system users. So if you imagine on a Unix-based box, you might have 10 Unix users that all map to one Postgres user. You can specify a mapping like that using this pgident.conf. And then there's a pglog. That's not a config file. I'm not sure what that is. I think I was getting at the point is that inside of the data directory there's a pglog on Red Hat systems. So on Debian-based systems, all these configurations are in that etc Postgres directory like I was talking about. One of the things that to be really careful about when you're on a Red Hat-based system is don't modify the other stuff in that data directory. There's a lot of things in there that are really important, like your data, and you don't want that to be destroyed. So be careful whenever you're working inside of the Postgres data directory and you're modifying things inside of it. So as I mentioned, there are some Debian-specific configuration files. These are only exist on Debian, and these are for working with these different clusters. So there's a startup config that allows you to say if you want to have the cluster automatically started or whether you want to have it disabled or has to be manually started. pgctl, which just tells what options to pass to pgctl. Generally, you don't need it. Same thing with this environment option, the environment configuration file on Debian. I don't generally change it, but it's there if you need it to set some kind of environment variable before starting the database. There's also cluster configuration information inside of this common directory. So on a Debian-based system, there's actually a Postgres common package that's installed along with your all the different Postgres packages that get installed, and that provides this information about setting up clusters. So inside of the Postgres common directory, you can have different settings for how you want clusters to be created. You can also control which clusters are the default cluster for certain users. You can actually have different users have different default clusters so that they don't have to specify -- cluster all of the time. Users can also set that themselves through the environment variables that the wrapper scripts will respect as well. And then there's a PG upgrade cluster.d, which isn't really used very much, but it could be populated by extensions to handle doing upgrades from different across major versions of Postgres. So on Red Hat systems, there isn't quite as much in terms of Red Hat specific config files, simply because Red Hat doesn't have all of those same cluster helper scripts and whatnot. So mainly it's just the init scripts, which generally you don't need to modify too much. Thankfully, some of the things that you used to have to modify have been moved out of there. You don't have to specify the port, for example, if you want to do a different port on a Red Hat-based system. All right, so I'm going to talk about configuration. So these are configuration items that are inside of PostgreSQL.conf. So this is kind of what you might want to do when you're first installing a system. This is for 9.4 and earlier. 9.5 is a little bit different in this area. Unfortunately, this deck hasn't been updated to account for that. So just be aware of that. Read the release notes if you're looking at 9.5, and that'll cover what the differences are between the releases. The big one here is if you want to allow other people to access the system, like on a Debian-based system, it'll start up with only listening on localhost, and you'll have to change listen addresses to star to allow people to connect in from remote. So of course, on a Debian-based system, it starts up in a default secure manner. Checkpoint segments. This is what I was talking about with the write-ahead log. In 9.5, it's called min wall size and max wall size. So that's one of the big differences. There is no more checkpoint segments. And what that does, that just controls how much of that write-ahead log space is allowed Postgres is allowed to use. So again, that impacts whether or not you're having to do checkpoints more frequently than you should be. Checkpoint completion target. The default is 0.5, which means that if we have a 5-minute checkpoint timeout, we're going to try to complete the checkpoint, that is writing all of those changes out to the heap files or the file system, the data directory, in 2.5 minutes. My experience is that there's not really any point to waiting or to being that aggressive, I should say. So you might as well just go ahead and set checkpoint completion target to 0.9, which says, okay, so across 5 minutes, use like 4.5 minutes or so to complete the checkpoint during. I mean, in my 2 cents, we ought to get rid of this option, but for now, at least set it to 0.9. Effective cache size. So effective cache size is something that is not actually ever allocated. What it's just used for is it tells Postgres, it gives Postgres some idea, okay, how likely is it that the pages from this particular relation, this particular table or index, how likely is it that that stuff's in memory, right? If it's really likely that it's in memory, that's great. We're probably going to use an index-based scan. If it's less likely to be in memory, we may move over to doing a sequential scan instead. So generally, I would set this to about half of RAM, but you can actually look and see, okay, how big is your Linux file system cache? And if that's the only thing it's being used for, you can just set it to whatever that is. Max wall senders is set to 0 by default because it does take up a really small amount of resources. I generally bump it up to 3 because you have to restart the system in order to change it. So I find that it's better to just go ahead and get that set up ahead of time. That's what allows you to do things like PG base backup, or to have a follower, right, like a replication system. All right, when you're doing logging, the default logging in Postgres sucks. This is what I do in terms of just kind of real basics for an initial setup. So logging every connection to the database, every disconnection, those are pretty obvious. Log lock weights is actually not as obvious, but it's ridiculously helpful. So whenever the system is stuck between 2 different processes due to a lock, right, and it could be any kind of a lock. It could be a table lock. It could be a row level lock. After a few seconds, what we're going to do is run what's called the deadlock detector, right? The deadlock detector is going to say, okay, these processes have been stuck for a while. Are they deadlocked, right? And assuming that it's not deadlocked, which generally is what you are hoping for, Postgres will then, if you have this enabled, kick out a message saying, hey, I've been sitting here waiting on a lock for, a minute, just FYI, right? And that can be indicative of someone's gone in and started a transaction and acquired some locks and then is just sitting there, right? Idle in transaction, not doing anything. And those are people you want to go, you know, over to their desk and kick them, you know, kick their chair and say, get out of your transaction so we can have processes move forward again. Logmin duration statement is important because this, in milliseconds, what you're specifying here is, okay, if a query has gone longer than this amount of time, I want you to log it so I can go review it and figure out why that query took so long, right? 100 milliseconds is a really long time, especially when you're trying to load web pages for a database to be responsive. You really want databases to be more responsive than that. Log temp files is really handy because in the operations of Postgres, there are things that we do when we need to use a lot of, it can end up using up a lot of disk space, like a sort, right? So if we have an on-disk sort that's happening, what will happen is if you have log temp files set to 0, then any file that we create for temporary purposes, like doing an on-disk sort, for example, will be logged. That can also be very indicative of why a particular query was slow. Maybe I had to go, you know, maybe Postgres has a sort 2 gigs worth of data, right? That's going to take a little while for that particular query. And then log auto vacuum min duration, setting that to 0 basically says, okay, I want to log every single thing that auto vacuum does, which I find very helpful as well because in a lot of cases, you know, you see some kind of performance impact and maybe it's auto vacuum kicking in. This will log all that information for you about what tables auto vacuum's been vacuuming and what it's been doing. There's also a really important thing called logline prefix, which you would think would be set to something reasonable, but it really isn't. So this is what I use. It's pretty complicated. The slides will be posted. I'm not going to go through all of this since we have a lot to cover here, but that's kind of what I end up using. Collects all the important information. One of the new ones is application name. That's one that you may want to really look at and see if you have. If you're already running Postgres, you may not have application name logged. That's helpful. All the Postgres applications will set that for you. You can set that for yourself also. Whenever you're connecting to Postgres through libpq, you can set your own application name during that connection string, and then that information shows up in the log as well as in some of the informational tables inside of Postgres. All right, so here's PGHBA in a nutshell. Everything's read top to bottom. So here we have the different different connection methods here on the left. So local means a local Unix socket. You then have, you can specify a database, or you can specify all databases, the user, and then the method. If it's over the network, you have an address setting, and then there's a bunch of different options that you can set. Addresses can be either v4 or v6. They can include CIDR notation if you want. There's a special option called reject, which if you hit that when you're reading through the file, means Postgres will just kick you right back out. And so that allows you to kind of have cutouts inside of your Postgres config, your Postgres PGHBA.conf. In terms of the actual different methods that are listed there, these are the different methods that exist inside of the, that are supported by Postgres. Peer is what I'm talking about when I'm talking about Unix sockets. So that's, we're just going to ask the kernel, who is this person that's connecting? We're going to get back the Unix username, and that's what we're going to allow you to authenticate as. And then you can map that to multiple different users using that pgident config file like I was talking about. GSS is Kerberos. It's also SSPI on Windows. So if you're setting up a pghba.conf on Windows, you want to set it to SSPI. But if you're using it on a Unix box, Linux box, which hopefully everybody is, you're using GSS. Works really well with MIT or Heimdall, Kerberos. I've played with both and been happy with it. You can also integrate it with Active Directory. So Active Directory is actually Kerberos underneath. You can have a Linux box joined to your Active Directory domain, or you can have an independent realm that has a trust relationship between your MIT or Heimdall realm and the Windows realm, and that allows you to do single sign-on with Postgres, which is really, really handy. There's also the ability to do certificate-based installation or certificate-based authentication. This is using SSL client-side certificates. So when you're doing that inside of your pgident, what you're mapping there as the system username is the common name, and that's what you use to map to whatever you want that user to be allowed to log into on the Postgres side, whatever Postgres username. One of the things that's interesting that I've never played with, to be honest, is that, or that I've never done before, but it works just fine, is that when you're talking about GSS and Kerberos, the system name is the user at realm. So it'd be like, you know, sfrost@mit.edu or something like that. You can have that as a Postgres username inside the database if you want. You don't have to map it to a simpler name. I typically do, but you don't have to. You can set it to just be that, and I've seen people do that, and it's kind of interesting and works well in large environments where you have a lot of different people across a lot of different realms. These are some methods that work just fine, probably most of what you're using. I don't like them. I much prefer the stronger authentication methods I just covered. MD5 is your stock kind of username password. That's probably what most people are using. It works. It's not what I would recommend, but it does work. PAM is complicated, so the reason for that is that Postgres doesn't run as root, so you have to set up things like SASL-auth-d if you want to have Postgres be able to authenticate users using PAM or using your password files, etc passwd and etc shadow. Obviously, with that and with MD5, really you want to be using SSL encryption. I would say just generally you want to be using SSL, but that's just me. We also support Radius. For anybody who's got some old school stuff that's still doing Radius authentication, Postgres now has support for that. And then there's also the traditional password base, which is just like, password with SSL is like OpenSSH, right? I mean, you feed the password over to with password-based auth, you feed the password over to the server, and the server checks it against your password files, and you're in, right? So that's how that works. These are methods I don't really like. LDAP it gets a bad rep from me simply because I know that if you're running LDAP 99% of the time, you're running Active Directory, and you should just be using Kerberos with Active Directory instead of using LDAP authentication. There are some environments where, you're running Open LDAP, and you actually have an LDAP, and you want to be doing binds against it for authentication purposes. But the other problem is that, again, you're passing the credentials of the user through the system. Right, whenever you're using LDAP or password or MD5, the user's password gets exposed to the server. It has to. With Kerberos and GSS API, that doesn't happen, which is one of the really nice things about it. Same with SSL-based certificates. Ident just shouldn't be used, and Trust really shouldn't be used either. They're not secure by any way, shape, or form, in my opinion. I know some people have used Trust in the past because they think it's faster than MD5. Maybe it is, but I wouldn't recommend it at all because it literally bypasses any authentication and potentially allows you to log in as any user. So just be aware of that. So if you have Trust configured, you should go change it. All right, PG ident. So here's what I was talking about before, where you have a map name. That's what you can specify in your PGHBA. So you can have multiple different mappings depending on the authentication method that you're using. And then you have what's called an auth user or a system user, and then you have what your Postgres user is. So for example here, this Joe would be a Joe that's installed on the Unix system, right, for peer-based authentication with peer map. And that user on the Unix file system can log in as Bob. Realize that Joe can't log in as Joe with this configuration, right? If you want Joe to be able to log in with, as Joe, you have to specify another name, another row here that allows that, or you can use a regular expression. So here's a regular expression for the Kerberos mappings. So what that regular expression does is whatever you want your match to be, that's what we're going to allow over here on the right. So if I'm sfrost at snowman.net as shown here, this \1 with this regex will be sfrost. So that'll allow any user at snowman.net to log in as their short name to the system. This particular mapping also allows me to log in as the Postgres user. So here for a certificate mapping, like with cert name, this would be my common name inside of the SSL certificate that I'm using to log into the system. And that allows me to log in as this sfrost Postgres user. And that's how you specify map equals whatever map name you want to use on the authentication line inside of, or on the method line inside of pghba.conf. All right, next question. So now we're going to talk about running Postgres. So big question is always, is Postgres up, right? So there's a couple different utilities to use. You can use just the service command to check status, and that'll, tell you, like it's on a Debian-based system, so there's multiple different instances, and for each instance it'll list whether it's online or not. There's a pgisready command that's available that you can use, and it is supported by the wrapper scripts in Debian, so you can pass the -- cluster option to it. And of course, you can always just connect with PSQL, which is very handy. the PG is ready is also available on the RPM-based systems, but it doesn't accept the -- cluster option. All right. So using PSQL. So if you're working with Postgres a lot of what you're probably doing, at least if you're a command line guy like I am, is using PSQL, right? There's a number of commands that PSQL takes. All the commands that PSQL, once you're inside of it, so this is like you're inside of the PSQL shell here, right? So inside of that shell, anything that starts with a / is going to be a command that's interpreted and handled by the PSQL binary. Anything else is like just sent to the server, and whatever the server comes back with, PSQL displays, right? That's essentially how it works. So the big thing is, you know, / is really helpful to get a whole listing of what the different options are. /H is ridiculously helpful because /H, what we do with Postgres is all the Postgres documentation has the syntax for everything that the Postgres server accepts, all the SQL that it accepts. All of that syntax is then stripped out of the documentation and included with PSQL. So you can do /H select, right, or /H insert, and you'll get the full syntax for that command. It's very, very helpful. You know, Control D or /Q to exit. Any queries that return information will be displayed to you, and /X can be used to do what's called an extended display, where you're getting a separate line for every column in the data set. So for example, this is what /X looks like. Table is a really handy command if you're not familiar with it. That's the same thing as select * from. It also accepts limit. It's very, very handy and allows you to have, you know, it's just shorter and simpler. pgstat_activity is a table that tells you what users are logged into the database right now and what they're doing. So here I've got expanded display on, so each line is actually a column, and each record starts with a record header like this. And then this is all the different information that you have inside of the database that you can access through PSQL about the users that are connected, such as, you know, what users connected, what their application that they're using is, if they're using one of the applications that sets that information, you know, the client information. So here there's no client address because I was connected in over a local Unix socket. When their process started, if they're waiting is an indication of whether they're waiting on a lock or not. The state is whether what they're doing right now, if they're running something or if they're idle in transaction. And then query is actually whatever the last query they ran or the current query that they're running is, sorry. So that's what the query ends up being. All right, so if you want to look at what databases exist, \L gives you the list of databases. I'm not going to go through all of the different PSQL commands just because there's a huge set, you know, slew of them. But that's what you can see with \L. It tells you the different databases. Pretty straightforward. Yeah. Yes. When you run PSQL, you go into a shell, right? A PSQL shell, and that's where you can issue / commands and then do selects and queries and whatnot. If you want to send a command to PSQL from Bash, right, you would do -C is the option that you pass to PSQL. So you can just do on the command line on a Bash line, you can do PSQL -C, you know, and then double quote select * from whatever and double quote, right? And there's a whole bunch of different options there for dealing with formatting, dealing with table alignment, dealing with headers and footers. So you can, you know, you can strip everything out and have like a select query that runs underneath of Bash, so runs PSQL, and just gets whatever that data element that you want out is, which is, you know, a lot of times what people are doing, and then you can shove that into a Bash variable if you want. Works just fine. Yes? It's a toggle, yes. Yep, \X, once you've turned that on, it'll stay that way forever until you turn it off. Yes? \? Is, you know, I think, I'm not sure what you mean by what command you're looking for. So what I would suggest, if you're not sure what the definitions of the commands are, like the queries that you're talking, you know, if that's what you're talking about, I would say if you do just \H, you'll get a list of all the top level commands that Postgres supports, and then once you've got that, you can go to the Postgres documentation and look it up. All right, so templates. I'm going to cover this really quickly because we're already at 40 minutes and I've got a bunch of slides left. So templates are something that you can create, and then if you do a create database using that template, we just basically copy all the files from that templated database into your new database. So if you're creating lots of databases for whatever reason, and you have like a common set of stuff you want to be in all of those databases, create a template database, fill it with that stuff, and then whenever you create a new database, just specify with template to the create database command, and then that'll be pulled over. All right, creating users is very straightforward. It's create user on the command line, or you can do create space user inside of PSQL itself. So this is inside of a PSQL shell, and then you can set a password and whatnot. It's pretty straightforward. User privileges. So there's a lot of different user privileges that are really important. Super user is the big one. Don't give it out to just anybody. It allows you to do lots of different stuff. You can access the database in ways that you really shouldn't be allowed to, so be very cautious with that one. Create role is more powerful than just being able to create roles because it allows you to modify roles as well. So that's one that you don't want to just give out to anybody. Login is, by default, if you do create user, you'll get the login privilege. If you do create role, it's like a group, so you won't have the login bit. So if you've done a create role and you don't know why you can't log in as that new user you created, it's because it doesn't have the login rights. You need to go change that on the system. And you can do alter user to change that information. And if you're curious about how to use alter user, you do /h alter user. And then you'll get that information. I'm not going to hit on the rest of this stuff, but there's also replication for changing, for what users are allowed to connect in to run PG-based backup, or to, be as a slave system connecting in to pull data down to be, like a hot standby or a read-only replica. All right, roles. So roles are kind of complicated in Postgres. Roles are roles, users are roles, groups are roles, everything's a role inside of Postgres. So when you are thinking about how you want to do group membership, use create role, set up your groups that way, set up your users with create user, that way that login bit gets set the right way, and then when you want to add someone to a group, it's using the grant command. So you say grant Joe to, or sorry, grant, whatever the group name is, so grant admins to Joe, right? And that allows Joe to now have whatever the rights of the admin role have. Inherit's really, really important. What it allows you to do is that it allows you to automatically inherit the rights of that role. So for example, with the admin role, in fact, I'm going to go over right here. So with the admin role, you can set up, it up as no inherit, and that means that when you connect in, you don't automatically get all of those privileges. Instead, you have to actually do a set role to it. So this is how I like to set things up for kind of a pseudo-like mentality. Note that it doesn't ask you for a password. There's no way to get Postgres to ask you for a password on a set role right now. I think that may change one day, but don't get your hopes up. So you create this role admin with no inherit, grant Postgres to admin, and then create this user Joe and grant admin to Joe. So now Joe can log in. He's a regular user, doesn't have any particular, special rights, but he can do a set role to Postgres when he's ready to. So that's how, and then, so that's how that works. All right, grant and revoke. So this is going to kind of cover what I recommend changing on Postgres. So by default, Postgres comes with what's called a public schema that anyone can create objects inside of. I don't generally recommend that because that schema is in everybody's search path, so it can just get obnoxious by default. So I always revoke create on that schema whenever I set up a new system, and always have per schema or per user schemas instead. So whenever I create a user, I'm going to create a schema for them also, and then they'll have rights on that schema, and they can do whatever they want with that. And then if I have something I want to create to have available to everybody on the system, I'll go put that inside of the public schema. These are the different ways and different options for privileges on a system. Depending on what type of object it is, there's different options that are available. And you can go all the way down to individual columns when you're talking about select, insert, update rights. Functions are important to think about. Functions with, whenever you do a create function, by default, everybody's allowed to execute that function, assuming that they can see the schema that the function is inside of. And then you can also have what are called security definer functions. Those are like functions with a set UID bit, right? So whenever you call that function, the function is going to change rights that it's running as over to whoever owns it. whoever the owner of that is, and then that's who the rest of the function's going to run as. So be aware of that. That's how security definer functions work inside of Postgres. All right, so I covered a little bit of this already, default permissions for execute, for functions rather. Everything else is basically secure by default, right? So you create a table, nobody else has rights to that table until you grant them access to it, unless you set up default privileges on the schema. So you can set up a default privilege for either a role, for a schema, for a role inside of a schema, and that allows you to set it up so that when you create a new table, it will automatically have some set of grants that are allowed to it. You can also use grant on all, so if you want to grant some access to all the tables in the schema, you can use that command. If you're wondering how big your database is, this is pretty straightforward. This PG database size is a function you can call, pass it the database name, and then PG size pretty just makes it look nice. You can look at the size of individual tables using PG total relation size. Note that that particular command will actually include the size of indexes and the heap and the toast tables and everything. So that'll give you the total size. That could cross over different table spaces, of course. So both of these will go across any table spaces that are involved and collect up all that information for you. If you're looking at the size of the individual table, like you don't want to look at how big the indexes are associated with it, you can just use PG relation size. And that is what that'll give you. That'll give you just the size of that relation and not include the indexes. So here's handy little command if you want to look at what's the size of all the tables inside of a particular schema. How much disk space is this user using up, right? This is a way you can do that, assuming that you have per user schemas. All right, creating a table space is kind of tricky. There's a bunch of options you have to set up and things you have to get right. Some of the big ones are you have to have created the directory already. It must be empty. Permission's got to be 700 on it. And you have to specify the full path to the directory when you're creating a table space. Do not ever create table spaces inside of your data directory in Postgres. Don't mess with the data directory at all. Create table spaces somewhere else. Okay? Postgres is, feels like it has control and domain over everything in the data directory. Don't be creating table spaces in there. I've seen that too often, and I just have to bring it up. Also, I strongly recommend you don't use a mount point directly, right? Create a directory underneath of that mount point and then use that as your table space. In my opinion, that's just best practices, but I think there's some good reasons for it also. If you want to get information about the table spaces, that's \deb on your at your PSQL command line, and that'll give you the location. These ones don't have location information because they live in the Postgres data directory, so that's like varlib PostgreSQL 9.4/main on Debian. And then you can use PG table space size to get the size that Postgres thinks of all the objects inside of that table space. Dropping a table space, you have to have the table space be empty before you can drop it. There's some handy commands that allow you to move sets of objects inside of, from one table space to another. But you may have to actually connect to multiple different databases to move all the different objects or to drop all the different objects. And once you've dropped everything inside of the table space or moved them out, then you can actually go and drop the table space itself. All right, file-based backups. So PG-based backup with wall receive is really, really handy for doing simple backups. That does require that max wall senders I talked about before. It's one time and it does the whole database, so there's no incrementals or anything that are available with that, which isn't great. And you have to have the write-ahead logs that were created during that base backup in order to restart the system. So when you run PG-based backup, there's an option there to stream or to pull down all of the X logs. Make sure you use that. I recommend the streaming option. JD did a talk yesterday. For those who weren't here, sorry, but he did a talk yesterday about more about backing up the database and using PG dump. I'll talk about that here in a minute. But one of the things that's also important is that this includes all the data files and all the indexes and everything. So when you do a restore, you don't have to recreate indexes or anything. You do when you're using something else, like when you're using PG dump, for example. So the other main one is using logical-based backups. This is where you use PG dump and PG dump all. These end up being essentially text-based dumps. They don't include any indexes or anything. The entire system has to be repopulated. All the indexes have to be recreated when you're doing a restore. So it's kind of painful. All right, backups don't work unless you restore them, right? So just best practice, make sure you're testing your restores, make sure you're actually doing restores and making sure that they work. Consider multiple different options for how to do a restore. If you're doing a restore with PG-based backup, it's pretty straightforward. PG-based backup creates a tarball for you. All you got to do is extract that tarball. All the data should be included. If you did the wall options like I was talking about, all the wall files should be there as well. And that'll have all of the data since the, any data that was created after the backup will be gone, right? Unless you save the write-ahead log and can replay the write-ahead log. You can talk for an hour just about backup with Postgres. So if you have questions about that, feel free to ask me. All right, PG Backrest is a really, really nice backup utility. It's available here, github.com, PG Masters Backrest. It's for file-based backups, and it handles all of the craziness about write-ahead logs and everything else is handled for you. You can do, and it also supports full point-in-time recovery. It's parallel. You can do differential and incremental backups. Really nice utility if you're looking at a large system. I strongly recommend looking at PG Backrest as your backup solution. These are the settings that you need to set to enable inside of PG Backrest. You can look at, or inside of PostgreSQL.com to use PG Backrest. You can find all that information from the PG Backrest web page as well. I'm not going to cover too much of it. This is how you configure PG Backrest. So there's a etcpgbackrest.conf file. There's a repo path, which basically says that's the path where all your backups and all your write-ahead log goes to. And then you need to tell it where the database lives. And then you can have multiple different clusters that are supported inside of one configuration file with PG Backrest. That's what main is here. So main is just like the 9.4/main, that's what main is here inside of PG Backrest. There's an info command with PG Backrest, which tells you information about the last backup. There's also a JSON version of this that gives you lots more data that you can then extract and parse and stick into a Nagios check if you want. And then speaking of Nagios, check Postgres for monitoring. So monitoring is obviously a really important aspect of database systems. Check Postgres.pl is a great monitoring tool for Postgres, integrates with Nagios. You can get it to dump out statistical information and have it be, graphed with pretty graphs and whatnot through Nagios and with Izinga or whatever you're using. It works pretty well. Also supports custom queries, which are really nice. These are the ones that I typically play with in terms of a minimum recommended set of checks to be running with Check Postgres. Sorry. Monitoring log files. So the same person who wrote Check Postgres also wrote tail and mail. So if you have you have Postgres log files, you do, right? It's nice to be able to monitor them and make sure that you're tracking any errors and whatnot. I like to use tail and mail to do that. It's pretty straightforward and it works quite well. You can also reconfigure Postgres to use what's called the CSV log. CSV log allows you to dump out the information from the Postgres logs into CSV files and then load those back up into the database. And there's lots of other options for doing your own rotation if you don't want to use log rotate. All right, configuring and tuning Postgres. Never seem to have enough time for this section. So shared buffers is this massive pool of stuff, of memory that we allocate whenever we start up. And that's kind of the Postgres local cache, right? So that allows us to avoid going back to the kernel and going back and forth whenever we need to get data off of disk or out of the cache. So it's really tricky to tune right. If your working set is less than the amount of memory you have in the box, I generally recommend setting shared buffers up enough that you can have your entire working set in memory, or maybe your entire database in memory if it's small, and that works out really well. If it's larger than that, I find that it can be helpful to actually have shared buffers be less, significantly less, down to the point of being only maybe a gig, right? And what that does is that means that we're going out to the kernel a lot more, but it also means we're doing less double caching, right? So whenever we have our own cache and the kernel has its cache, there's a risk of double caching there, right? Which just ends up wasting memory. That memory could be better used for running queries and doing other things potentially. Workmem is the setting that we use to figure out how much memory we're allowed to use with this query. So it's more complicated than that, but just realize that if you up workmem more, queries will be allowed to use more memory for doing things like building hash tables or doing sorting. So it can be really, really helpful. The default used to be 1 meg. We just upped that a little bit. I think it's like 8 now, so which is Better than 1, but it's still pretty freaking small if you ask me. So I tend to bump this thing up pretty well. The only downside to it is that if you have lots and lots and lots of connections, you run that risk of running the bit system out of memory. Realize that Postgres is actually very good at handling issues when it comes to memory. All right, I got 5 minutes left. So it's actually not like the end of the world if Postgres ends up using all of the memory in the system, because it'll get a memory error and it'll clean up everything very nicely. So it's not like a huge problem. Don't run out of room for pgxlog though. All right, maintenance work mem is what we use to create indexes. So you want to bump that up whenever you're creating indexes, but realize that we're going to use all of that memory. So just be careful from that regard. But it can make index builds go much, much faster because we have to basically sort everything. I talked about effective cache size a fair bit already, so I'm not really going to cover it again. Auto vacuum, that really washes out the screen. I'm sorry about that. So auto vacuum, the defaults generally are too low in my experience for a high transaction rate system. Usually what you want to do with auto vacuum is actually make it more aggressive, not less aggressive, right? What you want to do is you want to turn it up, get it running more frequently, because those more frequent runs will end up running for less time, right? And it'll also be cleaning things up in a more expedient fashion. So these are some different ways you can do that: decrease the cost delay, or just completely turn off the costing model, and increase the number of workers. Definitely, if you have a very busy system, increasing the number of workers allows it to work in parallel across more tables. Managing connections, you can bump max connections up. I had some folks that were doing it up to as much as like 500. It's really too much in my opinion. Really where you want to have max connections is you want to have the number of connections that are actively working in the database on par with the number of CPUs you have in the system. Generally speaking, that's the most efficient way of running a database server. One of the ways you can do that is to use what's called PG Bouncer, right? PG Bouncer allows you to have, is a connection pooler, which allows you to have all your applications can connect to PG Bouncer, and then PG Bouncer will manage those connections to the database and will basically multiplex on top of those database connections. So it's a very effective tool. PG Pool also works. Watch for idle, and especially idle in transaction processes. Those are bad. Because if it's idle in transactions, that means that there's certain processes that we can't move forward with, like auto vacuum and vacuuming and cleaning up dead tuples. Almost done, folks. Managing locks. So generally speaking, if you have a lot of objects in your system and you're using a pgdump-based solution, pgdump has to actually connect and lock every object that it's going to dump out, and that can end up being expensive. So a lot of times I'll actually end up bumping this value of max locks per transaction up some so that there's enough locks available for a pgdump-based backup. A heavyweight lock is required for every object that's accessed by a given process when it's connected. So not just pgdump, but your applications as well. Generally, your applications aren't accessing that many different tables at a time, so it's not that big a deal. But be aware that we do take out a lock. I say heavyweight here. That's a Postgres terminology thing. Heavyweight in this sense means that it's a full level lock. It doesn't mean that it's actually blocking anything, right? Access share locks don't block anything except if you want to like drop the table or something. All right, checkpoints. I talked about this a little bit earlier, but just make sure that your checkpoints are happening due to time. And if you have that log checkpoints option turned on like I was talking about earlier, every time we do a checkpoint, it'll say why it's starting, and it'll say when it finished, and it'll give you a bunch of stats about how many pages it had to write out, how many write-ahead logs there were, that kind of information. The big thing is make sure it's always starting based on time. If it's starting based on xlog, you're writing more xlog than you have your system configured to be able to write out to disk in time. So you want to make sure that you basically, that means bump up checkpoint segments, generally speaking. The larger the checkpoint timeout, a lot of people change checkpoint timeout because you reduce the number of full page writes, and it also does some other things that are nice in that regard. But the higher up it is, the more write-ahead log that you may have pending when your database crashes and has to restart. And what that means is that the database will take longer to restart because it has to replay everything from the last checkpoint. So if your database crashes and you have checkpoint timeout set to 5 minutes, it shouldn't take more than 5 minutes for us to restart. If it's set to 30 minutes, it could take as much as half an hour to restart. PG Badger is really helpful and handy for generating reports about queries. So if you're curious about what the query time information looks like against your database, I strongly recommend PG Badger. There's some configuration options. You can find it all on the web. All right, I have 5 seconds for questions. I will be at a bar somewhere, or you can find me after this if you have questions. I'll be happy to chat. Thank you. The slides will be up. I'll put them up on the wiki here in a few minutes. That's where I'm going to put them, yeah. Yes.
Testing, 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 testing. Seems good. Okay.
Test, test.
There we go. Yes, I'm going to be talking today about Explain, which is PostgreSQL's primary tool for query execution, query planning and execution analysis. It is an extremely powerful tool. It is also somewhat unintuitive, hence the presentation. So first, let's talk a little bit about what Explain is. Explain tells you a number of things about your queries. It tells you what the query planner planned on doing, how it planned on executing the query, and then gives you some statistics, depending on what mode you do it in, some statistics on what data it expected and what data it got, and can often tell you which step in the query took the longest. But Explain doesn't do everything for you. It doesn't, for example, if you're saying, why didn't it use that index? That's not something you can get out of the Explain plan. Sometimes you can infer it from the Explain plan, but you can't get it out of the Explain plan. It doesn't tell you how to rewrite your queries to make them faster. And it doesn't say anything about other factors that may make the query slow. For example, you will sometimes find that the majority of your response time in a query, like one of the things that I find all the time when I do analysis is, I look at the Explain Analyze in Postgres, but I also look at the response times reported by the application. And you can have a query where Explain Analyze says it's being executed in 50 milliseconds, but the response time in the application is 3.5 seconds. And that's actually because that time is being spent in data transmission or network problems or rendering on the application. That's not uncommon at all. And Explain won't tell you that. It'll only show you the time spent inside the database. And it won't tell you, and it particularly won't tell you, for example, things like data transmission time. Because if you request 150,000 rows from the database, that is going to take a significant amount of time to go across the wire. And that, again, does not get shown in Explain. So it doesn't tell you everything, but it does tell you a lot of things. So now, I did say that Explain is a little unintuitive to interpret. So in order to understand what Explain is showing you, I need to actually explain a little bit about how the Postgres query planner works. Because how the Explain output appears is really tied to how the query planner works. So what happens with the query planner is it takes the parser has parsed your query by the time the query planner gets to it and rendered it into a canonical form. And so the query planner breaks that down into individual atomic units of work that are called nodes, appropriately enough. And then the query planner comes up with every possible different way it could execute each one of those nodes. And then it chains those nodes together, and that will involve some discarding possible execution plans because they can't be chained together. And then it will take those chains and estimate a cost of executing that particular chain, and whichever one has the lowest cost is the one it'll pick, and that's the one that it'll display to you. I'm told, this was before my time, this was back at UC Berkeley, that our query planner was originally written in Lisp. If you look at the code, you can kind of believe it. It's very recursive and uses a lot of lists of things. But you really have to kind of understand the node concept to see what the Explain is showing you. So I mean, the basic idea of the nodes is, for every node, right, you have two inputs. One input will be one or more row sets. In the case of joins, it will be more than one row set. In the case of other forms of operation, it will be a single row set. And a row set is a synthetic set of data that might be a table, and it might be data coming from another query node. And then parameters that go into that node that define what the node is supposed to do, how it's supposed to execute its thing. And then what will come out of it is another row set. And that's what the query planner is showing you. So for example, if you had a sort node, right? You're doing a sort on a column, right? So what's going to go into that is some scan rows, and then a list of sort columns and how you want to sort on them, or sort expressions. And then what's going to come out of that is a sorted row set. And that's going to be the text that Explain gives you. Now, I've also mentioned here several times the term cost. So Postgres has what's known in the database world as a cost-based optimizer, as in we try to estimate the cost which is generally sort of an estimation of time, because that's what people care the most about is response time, right? It's generally sort of an estimation of time that it's going to take to execute the query, and pick, again, the plan with the lowest cost, right? Because everything else being equal, you want the query plan that's going to give the shortest response time. But it's important to understand that these cost units are completely relative. They are not meant to represent anything external to the query planner itself. As a matter of fact, costs between different queries are not even necessarily corresponding. Like, you can pretty much guarantee that a query that has a cost of 10 million is going to take longer to execute than a query that has a cost of 1,000. But two completely different queries, one that has a cost of 1 million and one that has a cost of 1.5 million, you can't make any assumption of which one is actually going to execute faster. The only thing that cost is supposed to be comparable to is that for the same query, the higher costing plan should execute slower. And then in cases when it doesn't, those are cases where we want to tweak the query planner or the statistics or other information in order to make the costing correspond better with reality. Now, that being said, Postgres has this parameter called sec page cost, short for sequential page cost, that people do like to manipulate in order to try to get that cost number to correspond more closely to, say, milliseconds of execution. But it's still an estimate, and it's still not scalably comparable. So you can only get extremely approximate that way. I regard that as a waste of time, because you're trying to actually make one thing represent another that it doesn't. So let's actually look at some of that. So here we have a very simple query with a very simple query plan, right? We're going to, these are all out of my sort of fake public library database called libdata that I have on several projects on my GitHub. And we're doing it very simple, right? We're looking up a patron by their indexed library card number. And Postgres is going to implement it in a really simple way. It's going to look on the primary key index, and it's going to retrieve our one row. So now, one of the things, the most important thing, like the very first time you jump on Postgres IRC, and you say this query is slow, and you post an explain plan, the first response you're going to get, how many people have done this? What's the first response you get when you do that? The first response you get is, please run an explain analyze. Because here's the thing. Explain by itself shows you what the query planner planned to do. Explain analyze shows you how it came out. That is, I expected to retrieve 1,000 rows from this, but I actually retrieved 10,000 rows. I expected this to cost X, and this is how much time it took. So explain analyze actually shows you that. Now, it's important to know that explain analyze does actually run the query, because without running the query, we can't find these things out. That's critically important if you're trying to analyze a write query of some kind, like an update or insert or whatever. It will actually do the update or insert. Explain analyze will. Explain will not. Explain analyze will actually do the update or insert. So if you're going to do that, it's important to do it inside a transaction so you can roll it back. Give me just a sec. So here's an explain analyze, and you can see the extra information that we have here, right? We have our index scan, and we still have our cost information and that sort of thing. And by the way, I'm going to go over this in detail in a minute. And then we suddenly have these actual time figures and actual rows. And then in more recent versions of Postgres, this is from 9.4, you get other information, like how long did it take to plan the query. Now, one of the things you'll find in very simple queries like this, the planning time is actually greater than the query execution time. That's not uncommon in queries where you're retrieving one row based on an index where the entire execution time of the query could be measured, is measured in the tenths of a millisecond. And right here we see this actually, it took us more than twice as long to plan the query as it did to execute it. So you get a lot of good information that way. Now, you pretty much always want to run explain analyze, because explain by itself, you're going to get what the query planner considers the most reasonable plan. And most of the time, the query planner is right. one of the big cursors from a Postgres development standpoint, one of the big problems with the query planner is that it is write so often, because it makes us very reluctant to mess with it. Because if we start messing around with the internals of the query planner, what we're going to initially get is a lot of really bad queries until we like retune it. So it's right most of the time, and so for that reason, the just looking at the explain plan by itself doesn't necessarily tell you anything. You want the explain analyze. Now, there are a few reasons why you wouldn't run explain analyze. Obviously, the update case is one. If you can't wrap it in a transaction, roll it back because of locking or whatever. The other thing is, maybe the query is so slow it never finishes, right? In which case, you can't run explain analyze because it never finishes. Maybe you just want to check whether or not a particular index is going to be used, and the explain plan will tell you that. And maybe if you've got partition data, you just want to check which partitions are going to get hit by a particular query. You want to make sure that the query is partition compliant, so you're only going to hit the partitions that match. And again, a plain explain plan will tell you that. You don't actually have to run explain analyze. The whole rest of the time, you're going to want to run explain analyze. Now, there are some other options for explain that are useful. One of the big ones got introduced in Postgres 9.2, I think, is buffers. So if you add buffers, then it tells you information about how much data was retrieved from Postgres' dedicated cache versus how much had to come out of the file system. Now, because Postgres goes on top of the file system, it can't tell you how many things came out of the file system cache versus off of disk. You have to sort of infer that by how long it took. But at least giving you an idea of cache data versus read data gives you an idea of, hey, is this query really slow because we're waiting to read stuff out of the file system? Cost and timing are on by default. That's what you saw before. You can actually turn them off. The one reason why you'd actually want to turn them off is on some platforms, such as Win2K server, checking the system clock is really expensive. It is so expensive that it affects the query execution time when you're doing explain analyze, and thus gives you a really deceptive result. And so that's a reason to turn timing off. The other thing that we can actually do is we can change the format. That is, what I've been showing you up until now is the default format, the default sort of line-oriented text format for explain and explain analyze. But we also offer explain analyze in YAML, XML, and JSON. And actually, when I'm actually doing work, I use the YAML format a lot because it breaks out each different thing into a separate key value field, and I find that much easier to read. Plus, I can put it into scripting tools and then actually look for certain patterns. And then there's verbose. So let's actually show you a few of those. So this is an example of buffers. So one of the things that we're actually getting here, so we've got this and we're doing here. Now you notice when you want to add these extra parameters, you have to use this extended format. Explain, open parentheses, parameter, and then on or off, parameter value. And that's the extended format that we're adding for a lot of Postgres commands because we decided a while ago that we wanted to stop extending the SQL parser syntax all the time because that was becoming a real problem. So instead, you put these in parentheses. So it might be a good idea to get used to doing that anyway, even though you don't technically need it with analyze and verbose. And then we're going to go here, and I'm actually doing a select from people, and then I am doing a JSON search, because this is a JSON field, so I'm doing a JSON query on looking up certain key values in the JSON field. And then here I'm getting a lot of information, and here you can see what we're getting from buffers. So we're doing a bitmap heap scan on people right here. Bitmap heap scan means that we are reading data from the, actually this is a two-part thing. So the first part is we do the bitmap index scan, which means that we are reading the index into memory and then transforming it into a bitmap so that it can be manipulated and matched up with other query criteria. And then it says buffers here, right? As in, we hit one data page already in Postgres memory, and then we had to read 39 of them, which is fine. It's like less than 1K of data. No, less than 1 megabyte of data. Not really an issue. But then we go up to the bitmap heap scan, and we're hitting 18,000 in memory and then reading 70,000 out of the file system. So if this query was slow, that would be a pretty good hint that it's probably pulling data off of disk, and that's why it's slow. Now, here's a cut-off example of the YAML format. Obviously, since it's vertical, it would scrolls all the way down, but you can see how if you're looking for these specific statistics, it's a lot easier to read this. It's a lot harder to see the whole query because you have to do a lot of scrolling. But it's a lot easier to read the parameters because they're broken out into separate fields instead of being in a massive long line that wraps. However, I'm not using YAML format for the slides because being vertical, it just runs off the slide all the time. Okay, and then verbose actually doesn't give you a lot of extra information. It's possible in the future that we might add extra things that display when you're in verbose mode, but right now what verbose mode mostly does is, remember I said there's row sets going into the node and row sets coming out of the node? It gives you all the column names for those row sets going in and out. Where that's really useful, someone else wrote a query, they handed you that query, and the query lacks table aliases. So you're like, hey, where did this fname field come from? What table is that from? That'll tell you that. You can actually trace that particular column through its various levels of the query to see what table it originally came from. So you can see where it's missing an index, for example. As well as it. Obviously, it is verbose, so be prepared for lots of output. But it's useful that way. So here we can see actually, here's all of our output, all the output columns from each level of the query. And for example, one of the things that I would say here for this is like, hey, at this level of the query, we're actually getting all of the columns in the fairly broad patrons table, even though we're only going to display 4 of them. Couldn't we add a filter criteria to, couldn't we add a filter criteria when we're searching the patrons table and actually avoid manipulating some of the data? That sort of thing gets actually particularly critical when you have these giant tables that have 600 columns. Anytime somebody uses a select star, things get really slow. So that's one of the things that you get usefully out of verbose. So next we're going to talk about reading explain in detail. Before I go to that, does anybody have any questions about the options? Like I'm actually going to show you what each different clause means in just a minute. But does anybody have any questions about sort of the options for explain before we get to that? No, we're good? Okay, cool. So the first thing to understand about explain, and this is the hardest thing to sort of grok when you're first looking at it, is it displays as an inverted tree. And what I mean by inverted tree is that the thing that's executed first is the one that's indented innermost. So in this particular query, which has a join in it, this bitmap index scan on lone patron, so we're joining the patrons table against the lone patrons table. This particular bitmap index scan on lone patrons is what got executed first for certain definitions of first. Here's the important thing. When Postgres is waiting on I/O, it will attempt to go to other query nodes that it can execute in parallel. So you will actually have overlapping execution between nodes. No, we don't have full parallel query in Postgres yet. It's coming in 9.6. We don't have full parallel query in Postgres yet. So it's not really parallel. It's actually more of sort of an asynchronous request model, right? Where when we're waiting on other systems, then we'll go on to other stuff. So, but anyway, this is executed first. And then second, we have a heap scan on loans and an index scan on patrons that's being executed second. And again, like I said, we're going to have some I/O going on there. Because we have some I/O going on there, those two things will probably be executed more or less concurrently. I mean, it's context switching by the particular processor, but it's more or less concurrent. And then when those get executed, that all gets passed up to the join, which is the nested loop join right here. And that gets executed last. So we have first, second, third. So that makes it hard to read because, first of all, you have to understand that the innermost thing is getting executed first. And the innermost thing may not be on the bottom. Sometimes we have other stuff on the bottom, and you'll see some hairier queries with this as an example. And the things that line up margin-wise are executed more or less concurrently. So now let's actually look at what's in those lines of explain. So here's one line of explain for an index scan on patron's P key, right? Patron's primary key. So we've got the index scan right here. So the first part of it just tells us what is the operation we are performing in this node. So it is an index scan node. Those first, 2 words tell us what kind of a node it is. It's an index scan node. And then the rest of it will be some sort of a text phrase telling us what were the operational parameters of that index scan node, right? As in, an index scan node, what index are we using? We're using the patron's P key index. What relation are we scanning? We're scanning patrons. Now, depending on what kind of node it is, that text string is going to be structured completely differently, because if we were doing a join node, the information that we need is completely different from an index scan node, right? Then the second thing here is we're going to get some cost information. So one of the things that people always mistake is they say, hey, why is this cost thing 2 numbers? Why is this a range here? What does that mean? Does that mean the cost is somewhere between these 2 numbers? Well, what actually we're showing you here is this number is the estimated startup cost. That is, what is going to be the cost of launching this node at all? In the case of an index scan, what is the cost to get the first row from the index? And then the other cost is, what is the estimated total cost for executing this? So it's the second one you're generally concerned about. And then the next thing that we'll actually estimate for you is how many rows do we expect to return, right? And and what's the estimated width? And we'll talk a little bit about those, more in a second. We've got, first of all, we're expecting a startup cost of 0.28, final cost of 2.5, and again, these are arbitrary units. Estimated to return 1 row. That row is estimated to be approximately 24 bytes wide. That width becomes important if it's a really high number. Otherwise, you can pretty much ignore it. But if you're returning a whole lot of rows, or the rows are really wide, then just the sheer memory manipulation of moving those rows around takes a significant amount of time. So now the other thing important to know about these costs is that the costs accumulate upwards in the query plan. So here is our first query node, and it actually has a startup cost of 0, which probably means it's just a straight up table scan, which has no startup cost, right? We've got a startup cost of 0, final cost of 1.5. And then that accumulates up to the other nodes where we have, and you notice here, the startup cost on that is equal to the final cost on this. It's not a coincidence. It's because what Postgres is telling us is it can't actually start this step until that step is done. It needs the data from this one in order to do that one. Whereas this one, it does not need the data for the other one, and hence the lower startup cost. And then this one, again, has an even higher, but you notice it's actually starting potentially starting before any of these are finished. You'll often see that pattern when we're doing a scan or a join or whatever, and the stuff is going to a sort. Well, as the rows come in from the other node, if there is processor time available, Postgres will start sorting them. So, and then this is our sort of final estimated cost for the query. So now if you're doing explain analyze, you're going to get an actual line as well. And so the actual line has some other stuff. We once again, this time, instead of having a cost, which is arbitrary units, we have a time in milliseconds. So this is very fast, 0.015 milliseconds. Now, in this case, in the time, what we're generally showing is from the row set coming out of the node, what was the time to return the first row versus the time to return the last row, which is similar to startup cost, but not exactly the same. For this, again, is how many rows did you actually return? And then you've got this loops thing. So the reason why the loops is important is that there are certain things that Postgres will do, such as nested loop joins and CTE scans. We'll be defining this in a minute, where it might actually execute that same node multiple times in a loop. So the thing is, if you read this line, what you're learning is that executing that node took a total of 0.015 milliseconds, right? But in this line, we actually executed that particular node 1,258 times. So this time is the amount of time for one average execution of the loop. So the actual amount of time taken by this node is 0.015 times 1,258. It's one of those things that trips people up when they look at it. And this number of rows is the average number of rows returned from each execution of the loop. So the loop thing trips people up all the time because they look at it and they go, wait, why does this node start only seconds after this other node is finished? This other node is finished after 1 millisecond, and this one only starts after 2 seconds. What's going on? Well, that node was a loop. It actually executed 10,000 times, and it took 2 seconds to do that. Now, the other thing that you'll get in certain kinds of nodes, such as scans or joins or other things, is that you will get some conditions. For example, in an index scan, you'll often get filter conditions on the index, right? As in, hey, we're looking for this particular card number on the index. And so that gives you some extra information about what's going on, particularly useful if, for example, you're saying, hey, why didn't we use an index for this? Well, look at the filter conditions, see if the filter conditions correspond to any index you have. If the answer is no, then you already know how to fix that query. So I've thrown around the names of a lot of, well, actually, let me stop. We take questions real briefly, so we actually have gone over the little parts. Anybody have questions on the individual little clauses before we go on to node types? That's a column name. That is a column name right here. And that is a value that I supplied. Yep. Other questions?
So earlier you mentioned the width is the byte of the row or the
The width is the number of bytes in one row.
in one row.
Yes.
So if there are 10 rows, you will only show per row.
Yes. The question is, if there are 10 rows, you only show per row, and the answer is yes. So, okay. How many in time here? Oh, pretty good, actually. So let's go over some node types. You got a whole bunch of different node types in Postgres. This is a slightly incomplete list of node types, particularly if you're using Postgres 9.5, because one of the things that we do in Postgres is we add node types all the time. Certain Postgres extensions will add their own node types. The query planner is designed to be pluggable, and therefore, as long as you meet the node API for the query planner, people can actually add their own node types in an extension, and they do. So you may see things that aren't in this list. Plus, there were some that were added new to 9.5 that are not on this list, and other stuff. But these are the ones you can see most of the time because they're the oldest ones and the most common ones, right? Most common, first of all, SecScan is our obscure term for a full table scan. Sec is short for sequential, and it means that we're doing a sequential read from disk. So that is the Postgres cryptic term for full table scan. Is SecScan. SecScan is something that you want to see in a very small table and you don't want to see in a really large table. Index scan is scan the index and look up individual tuples in the index in the sort of normal index tree transversal way. An index-only scan is, so one of the confusing things about Postgres, how many people were in Quinn's talk yesterday morning? So one of the things Quinn went over is how Postgres does in-place concurrency. Because rows are not deleted from Postgres immediately, they're marked as invalid for a certain range of transactions and then garbage collected later. Well, so at any given time, Postgres has to check what are called visibility rules to determine if you can see certain rows or not. And the visibility rows are stored in the base table. However, starting in Postgres 9.3, we said, hey, if all of the data in the table is really old, then we don't actually have to check visibility rules. And so we added index-only scan. And index-only scan is really nice if you're getting sorted output from a really big table, because it means all we do is retrieve data from the index and we don't touch the base table at all. You won't see it as often as you would like to see it, but it's in there. Now, bitmap scan is scan the index and then build a bitmap of which rows correspond to our criteria. One of the primary reasons to do that is I'm going to scan a second index or an index in another table, construct a bitmap, and then I'm going to overlap the two bitmaps in order to see which rows correspond to complex criteria. This is how Postgres can combine using 2 or more indexes on the same query, something that certain other open source databases can't do. Most of these kinds of scans will contain a filter condition. Obviously, sometimes you do select star from table. Particularly if it's a small table, that's not going to have a filter condition, but most of the time you're going to be select star from, select columns from table where, and that where clause is going to become what's known as a filter condition, showing what you're getting. But do keep in mind this is a node, per node thing, so sometimes the filter condition will be something that was generated by the query planner or executor based on criteria passed elsewhere in the query, and sort of bubbled up. So here's an example of a bitmap scan. And this is where I said visibility rules. So we actually have 2 steps here. We've got the bitmap index scan. And so this is where we scanned the index, and we looked for all of the items in the pages in the index that corresponded to that particular library card number, and constructed a bitmap. Now, the problem is that even in the bitmap index scan, we do have to check visibility rules. And in order to do that, we have to do a bitmap heap scan. And heap is, again, another cryptic term for base table. So we do the bitmap heap scan to actually double check that all of these rows correspond to our visibility rules before we proceed on to the next step. In this particular operation, the bitmap index scan, you will often find that the bitmap heap scan takes longer than the bitmap index scan. That's because the base table is much larger than the index, and it's not ordered. Yeah?
In that scenario, is it the primary filter condition already eliminates some of the stuff that you need to catch in the heap, right?
Right.
It's just a secondary check.
Yes. So what's happening is we're getting all of the rows. So the index does not have visibility information. So we're getting all of the rows in the index that have this card number. And then we're checking those rows and only those rows in the heap. In the table, that is. So join types. Postgres supports lots of join types in order to have different strategies to see which join. Nest loop join. Nest loop is the join that's most intuitively understandable, which is for every row in table A, look up all the rows in table B and loop over them one at a time. This is the fastest join strategy when very small numbers of rows are involved because there's almost no startup cost. It is a terrible strategy when there are a lot of rows involved because it is completely serial and there's no batching. So if we're joining some big tables, Postgres is going to try to do some other things, like, for example, a hash join, right? Where we actually make a hash map based on one table and then shove stuff into hash buckets from the other table based on which hash bucket they fall in and then sync them up. Whether or not a hash join is used is often dependent on how you have set the parameter work memory, because that defines the largest hash map you're allowed to have as a query operation. So if you think Postgres should be using a hash join and it's not, one of the things you can try doing is bumping work memory. A merge join says, hey, I'm going to want sorted output from both of these. You often see the query planner doing this when it knows you're going to be sorting afterwards, and that sort corresponds to indexes that you have in both relations, right? So if I have an index on first name here and an index on ID number here, and I'm going to be, or actually I have an index on ID number here and an index on ID number there, and I'm going to be displaying them in ID number order, and they're both big tables, one of the things Postgres will do is say, hey, I'm just going to sort everything according to ID and match everything that matches up, like a big zipper. You don't see that as often as the other types because you really need to have certain query conditions for that to be the efficient plan. It has a huge startup cost, but if you're joining a big row set against another big row set, it's often the fastest plan. More joins, because like I said, we support lots of joins in Postgres. Lateral join is most often used against what are known as table expressions, that is, functions that return a table. And you want to actually pass in criteria from one table, like a scan on a table, and you want to take the results of a column from that scan and pass that as an input to the function. So what you do is what's called the lateral join. It's really funky syntax. A lot of people can spend years on Postgres without using it, but when you do need it, it's really useful. And that is a separate type. A semi-join, this is how we execute outer joins a lot of the time. You know, as in, hey, we're only going to join against the rows that match in this table, and we're going to ignore the ones that don't match. You know, we're going to ignore the null ones, right? And the opposite of that is the anti-join. That's when you do, say, a not in expression or where not exists expression. We will often do an anti-join. So, some examples, again, so this is joins. Now, we have a hash join here, right? And one of the things I mentioned, there are the conditions. So, in the join, the condition is you're going to find the matching conditions between the two tables or relations or synthetic row sets or query clauses that you're joining, right? So in this case, we're matching the STL source ID against the source.id in the other table. And merge join the same, right? Here, merge join, we're matching this against that. I pulled these off of explained EPSAs, which I'll show you in a minute. And you can actually see some things that are happening. Like, for example, you notice one of the reasons that a merge join is being used here is because what we have is we have two giant, huge tables. We've got a row set of 30 million here. But the resulting, and you can actually kind of see, you know, how this filters out. But that's actually, you know, examples of some of these node types. So, more node types. These slides, by the way, are online if you want to review them later on. So I don't expect you to memorize all these. Aggregates. One of the things we do in Postgres is aggregate, right? Sum, total, average, median, standard deviation, all kinds of other things. So when you see an aggregates, group aggregates, that's our basic aggregate. Again, fastest way to do things on small row sets. Just, you know, go ahead and add up the values, and when they don't repeat, you know, do a new value and that sort of thing. A hash aggregate says, okay, we've got a lot of data, so we're going to construct a hash table out of these values, and then put stuff in hash buckets and group them that way. Much faster for if you're going to have a lot of rows, but your aggregation column is indexed. We'll do a hash aggregate. Window aggregates are used to support windowing clauses. How many people have used windowing clauses? Yeah. Those of you who haven't probably should. They're awesome. They allow you to do something in one query that would have taken 2 or 3. I'm not representing some of the new 9.4 aggregates in here, grouping sets, etc., which you'll now see as new node types. Or 9.5 aggregates, sorry. You'll now see as new node types. So, again, examples of that. So here's our hash aggregate. So we've got our usual execution time and cost, and then the criteria information we get here, right, is the key on which we are grouping, right? So these are the 3 columns, card no, last name, first name, that I'm grouping by, and we get that as our group key, and that gives us our condition information. Or in the group aggregate, we get the same thing. Other operations that you'll see expressed as nodes, although you know, they don't correspond to other things. Occasionally you'll see a unique. It's a lot less common now that we have other ways to deal with returning a unique row set that are less expensive, but occasionally you will as a way of deduplicating rows. And the primary things that'll produce this is select distinct and union as opposed to union all. And by the way, that's a query tip for you. If you're doing a union query and you don't have a good reason to deduplicate, then use union all because it is much less expensive to execute. The deduplication is expensive. But most of the time you won't see unique because Postgres will do something like a hash aggregate instead in order to implement this under the hood. A sort should be obvious, right? We're going to have a sort. Limit, if you're using limit or offset, that's the node you'll see is the limit node. Other operations, CTE scan, that's with clauses. So if you have a with clause, and then you have another query portion that is querying that with clause, you'll see a CTE scan node. That's our reference to the with clause. Subquery scan is the same, only for subqueries. And this is usually in cases where the results of the subquery can't be folded into the main query. We try to do that whenever possible. Because the thing that Postgres can do the fastest in terms of corresponding row sets is some kind of join. So one of the things that the query rewriter tries to do all the time is come up with a way of how can I turn this into a join. So if you're seeing something like a subquery scan, it's because Postgres couldn't figure out how to turn it into a join. Materialize. That's actually our most expensive sort of subquery or with clause, which says, hey, in order to actually execute this subclause, I had to actually turn it into a built, constructed complete row set in memory, which is expensive. And that's what materialize means. So if you're seeing a materialize step in your query, that can be a reason why it's slow. And then an append, and that's for like union all and partitionings and other things where we're appending row sets to each other vertically. So CTE scan example, we're going to have all kinds of things, CTE scan, and it's going to have this, and it'll refer to here's the name of the with clause, toe tab, and then there'll be a filter outside the CTE scan. And in recent versions of Postgres, you'll get this tremendously useful rows removed by filter. Because that rows removed by filter is actually the majority of the rows that were returned. You start saying, hey, is there some way I could push that criteria down inside the with clause so that I'm not doing all this expensive filtering? So, having done all of that analysis, actually, I can take like 1 minute of questions on the node types before we start looking at why is my query slow. Any questions? Yeah? Your statistics. Postgres keeps statistics on, I think I talk about this in why is my query slow, actually. So let's actually see. I think I talk about this in why is my query slow. If not, I will revisit it. So why is my query slow? So one of the things that you may have seen, you've noticed the background of my title slides here. Well, that background is this wonderfully useful tool maintained by Hubert out of Poland called explain.devsys.com. And what this tool allows, it's an online website in PHP that lets you paste in a query text, and it will kind of parse it out, and it will attempt to actually find certain things about your query that are common patterns for why it's slow, like a huge difference in the estimated number of rows returned versus the actual number of rows returned. It'll also tell you which step took the most time, right? Because one of the problems is, remember I said those costs and the times cascade upwards? Well, so it can take you a fair amount of math to figure out how long did this step actually take independent of the other steps. And so this will do that math for you. As you can see, exclusive versus inclusive times, right? So in this particular query, hey, this bitmap index scan is where I'm spending most of my time. And explain.devsys.com has highlighted that for me. So tremendously useful tool. Do keep in mind that it is somebody's public web thing. So if you have, data restrictions, you work at a HIPAA compliant, PCI compliant company, et cetera, you might want to pull down his source code for this and run it internally instead. He actually does have a button there to obfuscate all your column names. Yeah? I don't know. I don't really do any MySQL, so maybe? Yep. There are some other tools you can use. The SysAdmin GUI web desktop client will do a visual diagram of the query execution. I tend to find that only works for very simple queries because the diagram gets unwieldily large very quickly. There's a more sort of on steroids version of this, originally developed by Red Hat for Red Hat Database, and now maintained as part of the Enterprise DB Developer Studio. I haven't actually seen this because I've never used the EDB Developer Studio, but it's there. However, for a lot of people, their primary tool for helping interpret explain plans is the PostgreSQL channel on irc.freenode.net. Where people come in and they say, why is this query slow? And they post their explain plan, and then they get, please do an explain analyze, and they post their explain analyze, and then people are like, So particularly when you're learning how to interpret explain plans, the IRC channel is really invaluable. So here's some examples of particular query problems that you might encounter and how you'd actually get that out of the explain plan. So here's one where we simply need an index that we don't have. Because you can see here we're doing a full table scan. And we're doing a full table scan on a pretty large table, 200,000 rows. Probably full table scan is not the best strategy for this. It's certainly not happening quickly. And we've got this filter called category equals 7. Now, there's actually a little bit more to this query. I just sampled it out. There were other columns being selected, but the other columns were what you call non-selective. There were columns for which each value had thousands of rows. And Postgres will only use an index if it can pull a very small portion of the table, usually no more than a couple percent. Beyond that, it's actually cheaper to do the sequential scan. So the answer for this particular query was to modify one of those indexes to include this category column, and all of a sudden, the query got orders of magnitude faster. Another one example is bad row estimate. Now, I've actually futzed with the alignment here so that you can actually see this. And I didn't actually pick it out. So index scan and this sort of thing, and here's the cost. Here's the estimated number of rows returned from this. Here's the actual time, and here's the actual number of rows returned. Well, we're a couple orders of magnitude off. Now, these are estimates. I generally say anywhere within a factor of 5, that is 5 times as many to 1/5 as many, doesn't generally change the query plan. Sometimes it does when you're really close between two different cost estimates, but it doesn't generally. But things where you are 2 orders of magnitude off will change the query plan. And in this particular case, you know, if you're actually pulling 10% of the table, then an index scan is not the way to go. It's going to be slower than doing a sequential scan. So, and you can see where this estimate gets off. Trying to remember if I talk about statistics later. Anyway, we'll find out. Now, another one that you actually have here is I mentioned that loops thing, right? And this is where a lot of people miss the calculation, which is we're doing a nested loop query up here, and we're corresponding to 10,000 rows, which means that on this actual index scan that we're doing is we're actually looping over it, you know, almost 11,000 times. And that's what's actually consuming a lot of our time. That's why actually the end time for this is what it is. It's most of the time is being spent in that loop. And so you look for these things with very high numbers of loop values. Because usually there's a better way to do that. Now this is a complicated one, but it's really annoying because there isn't a good, easy way to fix it. So one of the things we implement in Postgres is this thing called abort early plans. And the way that an abort early plan works is, hey, you've asked for 100 rows from this table, and I don't have a good index to use, or I don't have, you know, or I'm joining against something else or whatever, but the criteria you've specified are very broad, and therefore, I think I can scan 1% of the table and get your 100 rows, and then I can quit. The problem is, if Postgres is wrong about how common your criteria are, or how well distributed they are, like say that your criteria are common, but all those rows are grouped somewhere down towards the end of the table, then it can end up scanning the whole table. So where you can actually see this here is, you notice this really weird circumstance. Look, the cost of this node is 9 million, and the cost of the node above it is only 2,600. Wait, I thought you said costs accumulate upwards. So the costs are accumulating upwards. Why is this cost this low? Well, the answer is Postgres is expecting to abort this join long before it finishes executing it. But if it's wrong, that can be a really slow query. And the reason why it's doing that here is if you look down a node and you say, hey, we've got this index scan backwards. So what happens is if you have an ascending index and then you ask for everything greater than x, we'll do an index scan backwards. And we expect that the index scan backwards, you see we've got this right here, 4.2 million rows on the index scan backwards. So Postgres is figuring that those index criteria apply to a lot of the table. But it's wrong. They apply to a much smaller slice of the table, which means we're going to have to scan a lot more of the table to find the 100 rows you were looking for. Now, I did say I would mention statistics. So the way that Postgres, the way that the query planner figures all this stuff out is that we have tables of statistics kept in the Postgres system catalog about what's in all of your tables. And these statistics are asynchronously updated. However, they are samples, number one. They're based on sampling the table because we don't want a full table scan all tables every time we update the statistics. That would be prohibitively expensive. So number one, they're based on samples. And number two, we're then applying algorithmic rules to those samples. So we have a list of the most common values. We have some histograms of ranges. We have some information on how unique values are in the column and that sort of thing. But because all of those things are estimates, they can all be off, right? So if you apply an estimate to an estimate, you get an estimate that has an even higher range of error than you did originally. So one of the things that you can actually do is mess with some of the execution of things. Now, the brute force way to do this is to actually force certain plans in Postgres by turning off certain types of node. So if you say set enable nest loop equals off, then you're preventing Postgres from executing a nest loop. Now, that is fine. That is great as a way to test different query plans. Like, hey, if this was a hash join, would it have been faster? Well, let's force that by disabling nest loops, right? And then you can see, hey, no, a hash join was actually much, much slower. That's why the query planner picked it. It was right. So it's useful for testing. The mistake that people make is that they actually change these things in PostgreSQL.conf. Because here's the thing, if you do that in PostgreSQL.conf, you're not disabling nest loops for that one slow query. You're disabling nest loop for every query in the database, which means a bunch of queries that used to be fast will all of a sudden become slow. Don't do it. That's for troubleshooting queries only. Now, one of the things you can do that's more useful is I said that the statistics were based on sampling. You can increase both the default sample size and you can increase the sample size on specific columns. The default sample size is like 100 samples, which is very small if you're looking at a table that's got 50 million rows, right? So you can increase it up to 10,000 samples. Anywhere over about 500 to 1,000, I really recommend doing it on a per column basis, because if you're sampling, say, a large text column, that gets really large, and if you start bloating out the statistics table, then the statistics table itself gets slower, at which point all of your query planning gets slower. So you don't really want to do that, right? Do it on the columns that you frequently join on, for example. The other thing that you can do is that you can actually clobber the statistics in certain ways. Indistinct is the estimation of how unique a column is. And because of, there's no such thing as a perfect algorithm for estimating indistinct from a small sample. So sometimes Postgres is way off based on how it took the sample. And the thing is, it's not that hard for you to get a better estimate of indistinct simply by doing a group by query one time. The indistinct of tables that have been in use for a while doesn't tend to change much over time. And so you can overwrite it with a set statement. And then you go ahead and run the explain again to see if it actually changed the query plan. And in this case, for our abort early plan, it did change the query plan by changing some of the statistics and saying, hey, you know, this abort early plan is bad because, hey, there's a lot more rows than you think. By increasing the sample size, we changed the histogram, and Postgres suddenly realized that more rows would correspond to those criteria, and therefore the abort early plan was a bad idea. Or, sorry, less rows would, and therefore the abort early plan was a bad idea. So that's your sort of cycle. So that's your basics of explain. So we have about 5 minutes for questions. So do we have questions? Yes, yes you do. If you're doing any of these statistics things, you have to run an analyze statement, or it doesn't take effect until the next analyze. So either you run an analyze statement or you wait for auto analyze to get around to it. Well, no, so the thing is, like, say you've got a B-tree index, right, that is a normal index on last name, or a B-tree index actually on date added, right? And then you want to see everybody whose date added is after a certain date. Then it's going to do a reverse index scan, because that's a descending search, but the index scan is an ascending order. I'm not entirely clear on why reverse index scans are slower than forward index scans. It has something to do with the data structures that we use. They are actually a little bit slower. So for example, if you are searching on greater than that date column all the time, you probably want to remove that ascending index and replace it with a descending index, because it'll be just a little bit faster. More questions? Question was whether or not you could force it to use a particular index. And the answer is no. We haven't implemented that in Postgres for a variety of design reasons. You can manipulate a bunch of other things that will end up causing it to use that index. And there are certain things that you can do with indexes, like Postgres supports the concept of partial indexes, where you do an index on where. Yeah. It's generally better in that case to actually look at why is it not using that index in the first place. Often, if the index really would be the fastest way to do it, and it's not using it, there's a good reason why. Like, actually, your criteria don't match the index as well as you think. For example, one of the problems that you'll have in indexes on text columns is mismatched text encodings. So you're using actually a different collation in your client than the database, than the column was populated with, and therefore we can't use the index on the text column. Or you're using, say, a like or unanchored text search, and you're using a like criteria, and the text column wasn't built there's this criteria called text pattern ops that you can apply to an index on a text column that makes it support like, and otherwise it doesn't unless you're in C encoding. There's a bunch of little things like that will actually prevent Postgres from using a particular index, even when you think the index is applicable. And then sometimes the index is actually slower. In that case, it would be nice to be able to force it to use the index just as an experiment, but we don't currently have a way to do that. So I did a tool a while ago, and I'm trying to remember where it is on GitHub, that actually looks through all of your tables, and then based on an estimate of how many rows it has in your tables, it takes all the columns that you've bothered to index, deciding that those are your important columns, because why would you have indexed them otherwise, and increases the statistics to a value based on a coefficient of that. I did that quite a while ago, though, and I don't remember where it is. Ping me later on, and I'll find it. Keep in mind that increasing the sample size in Postgres is not always beneficial, and it's not always size-based. That is, in a lot of cases where you want bigger samples is not because the table is bigger, but because it's more asymmetrically skewed. As in, like, if your data is completely randomly distributed, then you can go with a sample size of 10, right? It's when it's not randomly distributed that you need larger sample sizes. So in cases of highly skewed tables, right, for example, if you have a column that represents activity status, and then you're corresponding that against date, well, obviously the active rows are going to be mostly the ones with the latest dates. But Postgres won't know that instinctively, and so that having higher sample sizes. There's been various proposals to actually make the automated sampling correspond to a percentage of the table, but none of those have been incorporated into mainstream Postgres, because that would actually make more sense from my perspective. Yeah. One of the other things to understand is, until Postgres 9.6, we will not have any correlation stats between columns. So Postgres assumes that values between two columns are entirely randomly matched, which is a really problem when they are entirely non-randomly matched, like, say, month and year, right? Or zip code and state. Postgres will estimate way low on the number of rows returned from that. We are getting column correlation stats in 9.6 for some value of that, and that situation will improve a lot. But for right now, if you're saying, hey, I put criteria on two independent columns, and Postgres estimated really low, orders of magnitude low, it's usually because those two columns are actually highly correlated, but Postgres has no way to estimate that. And sometimes the answer can be making a multi-column index, which Postgres evaluates according to different stats. It doesn't, And sometimes there isn't really a good answer for that. So I'm going to take one more question, then we have to quit. Well, one more question? Okay, awesome. Thank you very much.
test. go ahead and get started. I'll be talking about all the big data science stuff that Postgres has as features and capabilities that maybe some of you haven't heard about. Talk about developer features, administration, performance. There's a community aspect to this as well, I think. And then finally, I actually have a case study for one of our clients that kind of shows how you can put all these different features together. So developers, there's a number of things that Postgres has that you can use to make your job of developing an application or developing predictive analytics models easier. The most obvious of which is the JSON data type. This was added in Postgres version 9.2, and there's been features implemented around JSON in every release since then. 9.5 gains the ability to actually go in and very easily modify parts of a JSON document without having to go through a bunch of extra work to split things out and bolt the document back together. There's two different data types, two different JSON data types that Postgres supports. The plain JSON data type basically takes your JSON and it stores it as text. So it keeps it in the raw form. The only thing that it really does is it validates that it is valid JSON. That's nice if you expect to be ingesting JSON and then not really doing very much with it. It is faster to pull data into that data type because it doesn't have to parse it. It just does a syntactical check. The second type is JSON-B, or binary JSON. That data type, when you provide it a JSON document, it actually goes and it parses it out and it stores the JSON in a compact binary format. So your original formatting and things of that nature are gone, but the nice thing is that the access to that data is then much faster. The other thing that you can do with JSON-B is you can actually index intelligently on it. There's two different indexing methods that are provided. One only operates at the very top level of a JSON document, but it knows about every single key. The other one operates on really at the path level. So it knows what paths are in your JSON. As I said, there's very rich set of very rich support for it. As of 9.5, there's 12 operators and 23 built-in functions for it. And importantly, there's also very strong interoperability between the JSON data types and other data types. So what I mean by that is you can do things like take a Postgres row out of a table and say, hey, take this row of data and turn it into a JSON document. It's a single function call. It's very easy. And whatever your input data is, you then get a valid JSON document out. And this is just one example of the kind of interoperability that you have with JSON. The next thing that Postgres features is an ability to really connect to everything that you could possibly want to connect to. Foreign data wrappers is the foundation for this. Those are added in 9.1. There are now just short of 100 foreign data wrappers. In fact, there's so many foreign data wrappers that there is a foreign data wrapper that reads the list of foreign data wrappers for you. There are 15 foreign data wrappers specifically targeting NoSQL technologies across 10 different NoSQL databases. And there are 7 that are targeting big data systems like Hadoop and HDFS. Now, if you need to talk to something that is not, that doesn't have a foreign data wrapper provided for it, first of all, it is not that difficult to produce a new foreign data wrapper, there are two projects. One is called Multicorn. The other is called, I read it yesterday and I can't remember the name of it. But basically what Multicorn does is you can write a brand new data wrapper in Python. There is, the other version of that is the same idea. It makes it very easy to develop a foreign data wrapper in Rails, in Ruby. Should all of those steps fail and you don't want to go and create your own foreign data wrapper, the next capability that you have is support for multiple procedural languages. And from the standpoint of interoperating with other data systems, this really gives you the world, because you can write code to run natively inside a Postgres database in Python, in Ruby, in Java, in all kinds of different languages. So whatever data you need to get at, there's a procedural language that will allow you to get at it, assuming that there's not a foreign data wrapper that you can use already. Again, because Postgres is so extremely extensible, you can, if you have a language that's not supported, like for example, I looked to see if the Go language had a PL language, and I didn't see it. So that might be an interesting project, is to add support for Go in Postgres. Finally, on the developer side, Postgres data types are themselves extensible. Perhaps the simplest version of that is a domain, which really is a data type that you put some additional checking on. You can also create a composite data type. So, for example, Postgres does not have a data type for complex numbers like Python does. But if you need to store complex numbers in Postgres, you can easily create a complex data type that just has your real and your imaginary components as two fields to a single data type. You operate on that as a single data type. So from the standpoint of data, it's one single number, but that single number has two components. You can also create brand new data types. Just last week, I decided, hey, let's see what it would look like to take a NumPy ND array, a Python data type, and port that into Postgres. And once I figured out, really most of the difficulty here was figuring out some compilation issues between Postgres and Python. In order to implement that data type, it's like 10, 20 lines of C code and 10 lines of SQL code. And here's a brand new data type now that you can make use of. In addition to the type extensibility, there was a feature added in, I think it was 9.4 or 9.5, called transforms. And these allow you to control how specific Postgres data types are relayed to the different procedural language functions. So, for example, the ND array data type, I created a representation function. Those of you that are familiar with Python will recognize the repr format. And you know, this is a function. It says, hey, I return text. I'm a Python language function. The important thing is the transform for type ND array. That tells Postgres, hey, there's a special thing I want you to do for this data type. So when you call this function in Postgres and you hand it an ND array data type, that gets treated in Python, it's an ND array data type. So all the Python function has to do is say, oh, well, here, I'm just going to return the representation, and that's what you get out. So all these developer features, ultimately, what they mean is that if you're working with complex analytical tasks, the last thing that you want to have to do is go learn a whole bunch of new tool chain, go figure out a whole bunch of extra stuff. You just want to be able to do your job and get it done and move on. And these developer features make that very easy for you to be able to do that. And any place where you see something missing and go, oh man, I wish Postgres did this, the extensibility capabilities make it easy for you to add something new that you don't have. And by the way, if anybody has any questions during the talk, please just raise your hand. I don't want anybody to wait till the end. So next up is administration. If you're going to maintain a big data environment, administration becomes a really key facet to this. And there's a number of things that Postgres has that honestly I think are actually superior to a lot of the big data options that are out there that are more traditionally used. A big one of those is backup. I think this is something that a lot of the big data tools, they just go, oh, the data set's so big. I mean, how can you back up 10 terabytes of data? Well, that data is your business. Most companies, if they lose their entire data set, just lock the doors because you're done. So I think that, dealing with backups, that needs to be a foreground thought. That needs to be something that you think of up front. And Postgres has done that. So there are two major ways to do backups in Postgres. Point-in-time recovery is really, point-in-time recovery is an extension of the same kind of crash recovery system that Postgres uses to deal with a server going down. So it uses the write-ahead log and takes that write-ahead log, copies it to a separate place, and that, in conjunction with just a plain old file system level copy of your database, that constitutes a backup. The really strong capability that point in time gives you is that when you need to do a recovery, you can say, okay, recover to this exact transaction. Because if you look at traffic on the mailing list and when people are asking about backup questions, I'd say probably half the time it's not because they lost their entire database. It's not because a file system just went kaboom and everything's gone. It's because somebody made a mistake and they said, oh, this table with test data, drop table test data. Oh wait, that wasn't test data, that was production data. And now you have this database that is all still there and it's up and running, but now you can't get to this very important data. So this point-in-time recovery capability makes it much easier to deal with those kind of situations because you can recover the database to the exact transaction before the mistake was made. The other backup option that you have is PG dump. From a big data standpoint, it's probably not what you're going to want to do. It has gotten significantly faster. It is now possible to run both a dump and a restore in parallel. Really the reason that I put it on the talk is depending on the criticality of your data, the thing that I really like about PG dump is it's basically impossible to screw it up. Point-in-time recovery, there's different ways to configure it. There's different tools you can use to configure it. It's very binary level. You can't do things like take a point-in-time recovery on, say, an Intel architecture and move it to a different architecture, which isn't as big of an issue today. But whereas PG dump, it's a SQL level dump of the database. So when you're thinking about disaster recovery, I would encourage you to at least ask yourself the question, hey, should we be doing periodic PG dumps as a last ditch recovery safety net? Replication with big data is interesting because a lot of times you're dealing with these very large data sets that you don't necessarily think, oh, I want multiple copies of it. But then again, a lot of times you're dealing with these data sets and tools that run in a sharded environment, and as part of the sharding, they keep more than one copy of the data. So Postgres, you can do the same thing. There's multiple different options that you can use to achieve that, and that gives you a lot more flexibility. Probably the easiest thing to set up is just simple streaming replication. So this builds on top of the same code base and the same concepts that are used for point-in-time backups, but it extends it so that now it's a point-in-time backup that's happening continuously, and at the same time that it's happening, you have a server that's restoring that backup and that you can run queries against. So you can stand up these replicas. They're very easy to stand up, and you also have the capability for these to be truly synchronous replicas. So what that means is if you have synchronous replication enabled, and on your master you do a bunch of work in a transaction and you go to say commit, that commit is not going to return to you until the commit record is recorded by the replica as well. So when that commit comes back to you, you know that that data is stored not only on the master, but also on your replica. And in 9.5, you can actually have multiple synchronous replicas. One of the other nice things about the synchronous replication is that you can control this on a transaction by transaction basis. You can have in fact, not only that, but you can have a transaction where you say, look, I just want the transaction to come back ASAP. I don't care if the data is on disk. So if you have tasks that need to deal with ingesting data at a very high rate, this is something very powerful because you can do the ingestion, get the data sent over to Postgres, and get an immediate return from Postgres, let your code keep going, gain more throughput without having to resort to actual, parallel processing or something of that nature, or something asynchronous. The other interesting thing that you can do with streaming replication is you can have the exact opposite of a synchronous replica. You can have a replica where you say, I want you to intentionally be 4 hours behind whatever's happening on the master. This is very useful from a disaster recovery standpoint because, again, if we go back to the scenario of somebody goes and they drop a really important table and now you have to recover, you don't have to worry about, oh, we have to get the backups, we have to stand up a recovery server, we have to start processing the backup. No, you have a server that's been doing all that. Now all you have to do is tell that server, hey, something bad just happened, so I need you to recover to this point and go do that, and as soon as it's done with that recovery, it'll come up and then you can pull the data off of there. Postgres also has logical replication support with a PG logical extension. This was just released not even a month ago, I think. It's very similar in nature to trigger-based replication, but the big difference is PG logical uses the logical replication framework that was first added in, I believe it was 9.4, that is based on the transaction log. So this is logical, quote-unquote, statement level or trigger-based replication that doesn't use triggers, so it's extremely fast. It is comparable in performance, in fact, to streaming replication. The other thing, so why would you want to use this? Well, one reason is streaming replication, you have to replicate an entire Postgres instance. All the databases, all the data, all the tables, the whole 9 yards. You have no choice in the matter. Logical replication, you can replicate only what you need. So if you have certain tables that, you know, a subset of tables that are hit heavily, you want to do some predictive modeling on them, things of that nature, you can take just those parts of your data, break them out to a separate server, and not worry about other parts of the database that aren't important and you don't need to support that workload. The other thing that you can do with logical replication is this provides a mechanism for doing a Postgres version upgrade where you can actually test out the new version of Postgres. You can run queries against it. If it looks good and you're happy with it, you can switch your production environment over to it, reverse the replication, so you still have your old version of Postgres, it's up and running, it's got all the current data. If the new version doesn't work out in production, there's a problem, you can switch back. The in-place version upgrade that is more typically used, PG upgrade, that doesn't have that capability. Even if you use the method of upgrading that copies all the data, once you've stood up your production traffic, well, now your old version is out of date. You don't have the same information. From a multi-master standpoint, there is now binary data replication. This builds on top of the logical replication framework. It's very similar, but instead of being truly ACID, as PG Logical is, this uses eventual consistency, and it supports wide area replication. There's a number of people that are running this where they have data centers spread across the planet, and BDR is very happy dealing with the kind of latencies that you get on those kind of internet links. The one kind of downside to BDR is that right now, for BDR to function, there's a few things that it needs within Postgres itself that are not in Postgres yet. So it is currently, it currently requires a slightly modified version of Postgres, so it's not 100% true community Postgres. Finally, there are other replication schemes that are out there for Postgres. Sloaney and LoanDeist are probably the two most popular. There's a few other ones that are out there. At this point in time, I would really tend to recommend that you don't use these ones unless you have a very specific need. PG Logical or streaming replication will most likely solve all the needs that you have better than either one of these would. So clearly when we're talking big data, analytic workloads, things of that nature, performance becomes very, very critical. And this is something that the Postgres community really puts a lot of emphasis on. There is a tremendous amount of work that happens to constantly improve Postgres performance. And I think that one of the really important things to understand here is that, you know, big data, there's all this focus on, web scale. We have to scale horizontally. And for a large enough data set, that's true. But there are a lot of data sets that Postgres is very happy to run on a single vertical server, and you don't need the extra overhead, the extra expense of colo space for, you know, 10, 15, 20 extra servers running around when you can get a single large server that will do the same thing. I've certainly run, I've personally run databases that peaked at over 6,000 transactions a second, and that was on a 4 terabyte OLTP database, running on, I think it was like a $20,000 server. And that was on I/O hardware that had problems as well. So despite some I/O issues, Postgres was able to scale very well to that. And that was version 9.2. The version number here matters because, as I said, the community puts a very heavy emphasis on continually improving the performance capabilities of Postgres. It wasn't that long ago where if you wanted to scale Postgres past 4 cores, it would ramp up to like 4, maybe 6 cores, and then you had this downward angle. Well, now it'll very happily do 80 cores. There are significant improvements that are made in every major release, and typically the number that I tend to go with as a ballpark is every major version of Postgres improves performance by about 20%. Now, obviously, that's very heavily dependent on your workload. Some people won't see a tremendous, they may see 5 or 10%. Other people are hitting a problem area, and they'll do a version upgrade and go, oh, holy cow, it's twice as fast. So why does this matter for big data? Well, data keeps getting bigger. It wasn't very long ago when a terabyte database, that was a big deal if you had a terabyte. Now, a petabyte is a big deal. So that's gone up by a factor of 1,000. And what allows you to manage that kind of growth is your technology platform basically has to grow faster than your data is. And Postgres performance improvements play a significant portion of that, because if you're getting 20% year over year from Postgres, that means you don't have to look at your own software stack and go, man, where are we going to get the next 20% from? Right. No, it's a very good comment, because a lot of the NoSQL solutions are very, very space inefficient. And it's kind of easy to dismiss that with, oh, disk is cheap, and yes, disk is cheap, but what's not cheap is the I/O. Alvaro, the creator of ToroDB, gave a talk a couple hours ago in the other room, and he's got numbers that showed comparing Mongo to Toro. Sorry, let me take a step back. ToroDB is the MongoDB wire protocol implemented on top of a relational database, specifically Postgres, though theoretically you could run any relational database. And the testing that they have done, they see that storing the same data in Postgres versus storing it in Mongo, it's anywhere from 68% of the size to 38% of the size. So when you get down to 38% of the size, that means that 2/3 of the data that was in Mongo was wasted space, basically. And that makes a big deal from a performance standpoint. So no, that's a very good point. It's certainly relevant. So finally, coming out in 9.6, after I don't know how many years of us wanting it, Postgres is getting parallel query execution. This is a tremendous amount of work that's been done by a handful of people. Right now it supports sequential scans. I know that there's parallel join execution. I don't know offhand if there's parallel index reads. I don't know if anybody here does. and it does support, or they're working on support for parallel aggregate operation. One of the things that people have a tendency to focus on with big data is this whole horizontal scaling. And admittedly, this is an area that Postgres is not as strong on, but there actually are options here. First of all is PostgreSQL. This is a fork of Postgres that allows you to run distributed transactions on multiple instances in a fully ACID manner. So from a user interface standpoint, it basically looks like, oh, it's just one Postgres instance. It just happens to be spread across a number of different servers. There are some other variations of this. In fact, PostgreSQL grew out of something called PostgresXC. So L comes after C. You want the newest one. There's also PostgresR. There's also Greenplum, which was very recently open sourced. PostgreSQL seems to kind of have the biggest weight behind it right now, so that's why I mentioned it specifically. The other option that you've got for sharding is a project called pgshard. And pgshard, I was going to put examples in and I completely spaced out and didn't do it. But basically, if you want to take a table with pgshard and spread it across multiple servers, you run one function to say, hey, this table, I want you to shard it on this field. And you then run a second command to say, okay, now that this is sharded, go actually spread that data across all the clusters that you have. Once you run those two commands, you write queries against that table, and they just get spread to all the different data nodes. There's nothing else that you really have to worry about. So very, very easy to use, very flexible. The only downside is that with spreading the data out, you don't necessarily have a truly ACID database anymore. So if you want to do updates, and in fact it does require that when you're doing updates you have to include the partition column in your where clause of the update. So really updates are not going to be ACID, they are going to be spread across multiple nodes. But as long as you are okay with that, it's a really good option for getting horizontal scalability should you need it. Postgres also has support for column stores. For certain workloads, certain data locality patterns, a column-oriented storage technique can potentially be a lot faster than doing the equivalent in a row-based storage mechanism. The CStore foreign data wrapper is I would say the most up-to-date version of this. It was created by Citus Data. It's basically one of the parts of their commercial technology, and they've open sourced it for the community to use. It is implemented as a foreign data wrapper, so that's kind of the interface into it. There is also an in-memory column store. There was a presentation on this at PGCon last year. And I did look when I looked it up. There is current activity in GitHub for this. So there were commits back in I think October. So there is activity on it, but I haven't frankly seen much publicity on it. So if you need a column store, I kind of included it for sake of completeness. If the CStore FDW doesn't do what you need, you might look at the in-memory column store. And there's also a foreign data wrapper to Monet, which itself is a column store database. Finally, on the performance side of things, Postgres has support for GPU utilization. For certain workloads, this can provide just tremendous speed improvements because GPUs are all based on this idea of take a single or a handful of small operations and apply them to an enormous set of data as fast as you possibly can. That's how graphics processing works. And for certain activities in a database, that actually lends itself very, very well. I would encourage you, if you're interested in this, go ahead, take a look at the wiki page. It's got some performance graphs on there. And admittedly, the performance graph is from an ideal best case scenario, but the speed improvement is orders of magnitude, like a factor of 100 or more. So if you're pushing the envelope performance-wise, this can be a great thing. And the nice thing is that it works natively. Once you load the extension, it just goes and does its thing. So if it sees a query that it thinks would be a good candidate for running on the GPU, it's just going to go do it. You don't have to sit there and manually hand code or anything like that. Finally, another aspect of this that I think comes into play is there is really a very large, very extensive community that has built itself around Postgres. And these are two examples that come to mind that I think are relevant to big data. This is certainly not anything comprehensive. PostgREST is a RESTful API for Postgres. So if you want to be able to treat Postgres kind of like if it was a NoSQL database and provide a nice, easy web interface to it, PostgREST will do that for you. Also, as I mentioned, ToroDB is the Mongo wire protocol implemented on top of Postgres. So to kind of put all this stuff together, you know, I've talked about a whole bunch of different features, just trying to kind of get you thinking about the different things that go into predictive analytics and data science and some of this big data stuff. Let's look at what happens when you actually put all this together. So in a traditional analytics environment, there's a number of different steps that get performed in order to go through the work of building a predictive model and trying to vet it out and trying to decide, okay, is this thing working, is it not? And really this is pretty painful. So the old school traditional way to do this is first you would do a bulk export import of your production data into an analytic tool like SAS. When you're dealing with a 4 terabyte database, doing this becomes painful. And then having to keep this thing up to date and having to do that every time that you need to spin a new version of the model, it kind of stinks. Once you've got it in the tool, now you can use the tool to start identifying correlations, patterns in your data, things to be looking at, and you use that information to start creating your models. And at this point, you're basically creating your model by hand. It's almost as if you're just writing the model as math formulas on a piece of paper. Once you've got an idea for, okay, these models, here's what I think is going to work, you'll do some amount of validation of the models based on the data that you've loaded into your analytics tool, but ultimately you're probably going to have to take this model and run a regression back against your raw data set, basically trying to simulate, okay, if this model was up in production when this event happened, what would this model have said? Would it have made a better decision than the old model did? And there's different ways that you can do that. The way that I've seen it done is that you take the model and you write it in pure SQL. And that can end up becoming kind of messy and difficult because even if the model itself isn't terribly sophisticated, if you're dealing with a model that's looking at, 50, 60, 70 different variables, you've got to hand code, well, how do I pull each one of these variables out? How do I present it? And then you have to run the calculation as well. And you're also worried about trying to do this in a way that's going to perform reasonably well so that you can, run this test and it doesn't take 3 weeks to run. So you go through some iterations of that and you use the information you gain to go tweak the model, change the parameters in it, things of that nature. Finally, you say, okay, I think we have a model. I think we're good to go. Here, Mr. Production Team, Mr. Application Developer, here's the model. Go code it. And now you wait. And you wait, and you wait, and 6 weeks goes by, and 8 weeks goes by, and finally your model makes it out into production. And now, 3 to 9 months later, you can finally see whether all this work that you put into this model is actually producing good work, if it's producing a significant improvement or not. And I've talked to people that do a lot more of the consulting in the predictive analytics space, and this is not uncommon. This is a very prevalent thing that you see, fundamentally because your data scientists and your analysts use a different set of tools and have a different set of needs and have a different way of thinking than your application developers do. Your application is frequently written in something like Rails. Well, your modelers may be using Python. They may be using R. They may be using something else that you wouldn't really want to try and write your web application in. This is the right tool for the analytics job. This is the right tool for the application job, and we have this big gap in between, and that causes problems. So when we started working with one of our clients, they needed to be able to do this stuff, and they've seen this kind of thing before. So they were already very much in tune to this idea of, look, we need to make this analytic workflow, this has got to be made easier because it just, we can't be spending 3, 6, 9 months on spinning models. So if you take a step back and you think about creating a predictive model, and especially executing the predictive model in a production environment, there's kind of two things that go into this. The first thing that you need is data. And, that sounds kind of obvious and silly, but I think it's important to kind of segregate that out and separate it out, because no matter what, the data portion of executing your model, it's a data problem. Whether your data is stored in a relational database, whether it's stored in Mongo, whether it's stored in React, wherever it's stored, the problem of how do I gather the data together that I need to make this prediction, it's a data problem. So the key facet there is solve your data problem using your data tool. So in this case, they are running on Postgres. Our methodology for pulling the data together is it's all SQL. We have a view that goes and pulls the stuff together, and then there's just a simple function that you call and say, hey, here's the person's identifier. Give me the data that I need to run this model. And the function returns a Postgres complex data type that is every single piece of data that is needed by the model. Some of that is very simple scalar data. Some of it is arrays that are actually arrays of complex data types themselves. So there's an actual nesting that's happening here where you have this multi-layer document essentially that's being handed to the calculation function. But in order to ensure robustness and to make sure that there's no surprises and that we know exactly what this data is and what format it's in, we're not using something as malleable as, say, JSON. It's done as an actual Postgres data type. So there's no question about what is being handed back and forth. So the data gathering is done in SQL. The calculation function, on the other hand, and again, we're keeping these two things separated very specifically. So now the calculation, you want to run the calculation in R? Hey, great, fine. You want to run it in Python? Okay, not a problem. You want to run it in Perl? What the hell is wrong? I mean, yes, we can do that. It doesn't matter. It'll run in whatever procedural language you want to. As long as Postgres supports the procedural language, you're good to go. And the nice thing is that these ideas have been wrapped up in a framework. So there's a set of database functions and tables that are built around this notion of here's the data stuff, here's the calculation stuff. And this framework does things like when you go to set up the next version of a model, you say, okay, here's version 3 of the fraud model. Here's the function that goes and gathers the data, and that gets put into the framework, and the source code of that function gets put into the framework. Here's the function that runs the calculation, and the source code gets put into the framework. So now we have this record that says, oh, here's the exact version, and every time we do a run of the model, we say, well, here's the model we're running. We capture all the input data. We store that as part of the execution, this individual execution. We then also hand this to the calculation function. It does its thing. It provides another Postgres compound data type. We then store the compound data type of the results. And now we have a record of absolutely everything that went into executing this model. Now, for a lot of you, out of curiosity, how many of you are doing big data? How many of you data science, data? Okay, good, about a quarter. You know, a lot of you, if you're doing like weather modeling or something like that, you're like, well, why are you going to all this problem? Why are you going to all this trouble? Well, Curios Capital is a lending institution, and there's a lot of regulations that are wrapped up around lending institutions. So when they're at work one day and the auditor shows up at the front door, they want to be able to answer auditors' questions. And part of this is the auditor can go in and pull individual loans or pull declined loans and say, why did you decline this person a loan? Did you decline it because they're a woman? Or did you decline it because their credit stinks? The first one is bad, the second one is okay. So this framework was developed specifically to support those kind of ideas, that now they can explicitly say, here's everything that went into this model decision. So those of you that are in a heavily regulated industry, those of you that want that traceability, you know, that's something that might be very valuable. Others of you that don't care so much about the traceability, a lot of that I think is still valuable. You know, this notion of separate the data gathering from the calculation, but even more importantly, utilize Postgres as the thing that binds this stuff together and that makes it easy. Because now, since all this stuff is done in Postgres, we can do things like spin up a snapshot of production, go mess around with the models, whatever. I don't care if you screw the whole thing up as long as you don't leak any sensitive data. You can go test on it. Oh, you think you got something up and workable? You want to do a regression? Okay, fine. Let's run the regression on a replica, say. Or we could even potentially run the regression in production itself and just not use it for decisioning. And the nice thing is we would be able to prove, oh, nothing's decisioning on it because there's no records that indicate it. I could easily put a trigger in place that says if you try and create a record, deny it. You know, so there's all this flexibility that comes about because instead of this data analytics team and the application development team, I'm standing here in the middle as the data architect saying, come on guys, let's pull this in together here. So finally, you know, one thing I do want to mention, obviously I'm a big Postgres fan if you haven't picked up on that. There is no such thing as a magic bullet. There was a tremendous amount of hype around NoSQL when the tools started coming out. And a lot of people were like, oh, this is going to solve everything. And you look over the past year or so, and all of a sudden now, there's all these projects that are springing up around taking a NoSQL technology and putting some form of SQL back on top of it. Because as it turns out, SQL is a pretty good language for dealing with data. Maybe you can't do all of your big data analytics, data science in Postgres. That's fine. You know, there are certainly workloads where Postgres is not the right tool for the job. It's not the right answer. What I do think that Postgres has to offer is this incredible amount of connectivity and this incredible flexibility through its extensibility and the capabilities that it already has built in, so that the parts that don't make sense to put into Postgres, fine, put it in the technology that makes sense, but then use Postgres as kind of your hub. Use it as the thing that can pull all this stuff together and make it easier to do your job, make it easier to work with. And of course, if you do have parts of your system where you really do care about immutable data quality, and you need to make certain that, hey, when I say this thing is committed, it's committed, whether it's because of regulatory reasons, whether it's because you're dealing with, you know, things like a shopping cart. If somebody buys something from you, I tend to think it's pretty important that when they click submit and you say commit, that record is stored, but when you show them the confirmation page, it says, yes, your brand new widget 5000, it's on its way. So, questions?
You said something about putting the algorithm, whether it's, let's say, a neural network or that machine in Postgres?
Yes. So, because Postgres has this support for multiple different procedural languages, you can run pretty much whatever you want to run in the database. Now, I will say that obviously if you've got something that's going to just burn through 80 cores like there's no tomorrow, maybe you don't want to run that on the database server itself. But you can also, because you've got this advanced language support, maybe what you're doing in the database is you make a call into a procedural function that itself can go call out to a more distributed environment, and then the data comes back in. Now, on its surface, that sounds kind of weird because, well, why wouldn't you just have the application do it? And the reason I would personally do it in the database is you're doing your data gathering, you run the calculation, you get the results back, you probably need to store the results in the database too. So really this is all still a data problem. It's not until you've captured the data, calculated, and then stored the results that now you go back to the application and say, hey, here's the number that you were looking for. Postgres does not, and I don't think it should, because it's got Python, just as an example. And I know that there's some nice neural net capabilities in Python. And you can pull those classes in. All you have to do is install the class library on the database server, and you can run it right there native within Postgres.
How do you end up distributing your workload?
Right. So again, this is where you do run into the trade-off of if it is something that is that computationally intensive that you're going to be doing, you may not want to run that directly on the database server. The question then becomes, okay, what's the data component of that look like? Like how much data are you dealing with for a model run? If you're doing something that's say, you know, finance-based or you know, something that's not handling enormous amounts of data, I think it's reasonable to say, well, hey, we've just got a Postgres database. It's got it. We pull it together and then we fire it off to an external process. And there is parallel capabilities within Postgres and cluster capabilities. On the other hand, if you're trying to do like weather modeling and you're trying to pull in, you know, every temperature sensor on the planet for the past week, okay, Postgres maybe not the right answer. So it depends on what you're trying to do. Really what I want to do with this talk is just get people kind of thinking, because I think right now there's this mindset of, well, it's a relational database. You don't, big data and relational, that doesn't mix. Well, it can mix.
Follow-up question, how sophisticated is the foreign data wrapper that we call FD7?
Yes. I do not know off the top of my head. Right, right. Right. I don't know, honestly. The thing is that I think, so when you talk about foreign data wrapper sophistication, at the base level, all that a foreign data wrapper is doing is it's just passing data back and forth. It's doing protocol translation, and it's basically turning something like a select statement into, you know, whatever you need over here. Where the sophistication comes in is when you're trying to do stuff like, okay, I'm going to join 3 tables locally and 2 tables over in this foreign data source and 3 tables over in this data source. So what's the efficient way to plan that and push that all out? That level of sophistication, I suspect, is not in the Hadoop foreign data wrapper, because that level of sophistication is still being worked on in the Postgres foreign data wrapper that lets you talk to another Postgres database. So that I don't think is there, but I suspect that for a lot of these tools, it's probably not a really germane question, because a lot of times they don't, you know, I don't think Hadoop even has the concept of a join. Maybe Hadoop does, but I know a lot of the NoSQL tools, what's a join? You know, you're pulling an individual document or an individual key. So I think there was some questions over here. No? Anyone? Awesome. Thanks, guys.